Give me just a second. Yeah, it's okay. So let's share my screen. Can you see my slide, please?
Yes, sir. Yes, sir.
Okay, thank you. Thank you so much. Today we'll discuss about the mitigation potential and the characteristics of urban greenery. Before we start discussing about the specific characteristics of urban greenery, and in order to understand really how urban greenery affects the urban climate, it is very important to understand really some basic notions of urban climate. We have repeated this in the past, but please allow me to repeat it again and just to remind you a little bit how really things move in the built environment and especially in the urban environment regarding, let's say, overheating and heat mitigation. The thermal balance in the urban environment is completely different than the thermal balance of rural areas. Why? Because we have anthropogenic heat, which is released by cars and also combustion systems. We have much more solar radiation, which is stored because, of the increased mass in cities. We have a blockage of the emitted radiation because of the urban canyons. And so this makes, the thermal balance of cities much more positive and, let's say, than the thermal balance of the rural areas. And we have to understand that in the built environment and in general, we have gains and losses. So in order to, let's say, increase the temperature in the city, we will have to decrease the gains and increase the losses. And losses have to do mainly with, let's say, the use of latent heat, which decreases the temperature, and also, with advecting forces, which also remove the heat from the city. So trees contribute mainly to latent heat, emit and release latent heat, which really decrease the, let's say, temperature of the city. At the same time, trees contribute really through shading to, let's say, provide comfort. Shading is not really decreasing the temperature, but is providing comfort because we are less exposed to solar radiation. So this means that we need really to make the balance, to understand the balance of the energy in the built environment. And this has to do first with the gains, and the gains is solar radiation, at the same time anthropogenic heat and whatever it is coming into the built environment, and the losses, which have to do mainly with the latent heat, the emitted radiation, and other things. Also, we have stored, let's say, heat. Stored, which is radiation, which is stored in the mass of the buildings, which is released a bit later. Given that, it is very important to start really understanding not only the energy, let's say, function and the energy operational characteristics of greenery, but also the general, let's say, environmental benefits of trees and of green infrastructure in cities. So green infrastructure in cities has several environmental benefits. The most important have to do with the production of oxygen, and oxygen is produced through photosynthesis, and we know that plants release oxygen, which of course is very important for the living organism. Also, trees contribute to carbon sequestration. The vegetation absorbs carbon dioxide, and this helps to reduce greenhouse gases and combat climatic change. Also, trees contribute to climate regulation. Trees and plants moderate local climate by providing shading, cooling the air, and of course influence the rainfall patterns. At the same time, Other environmental benefits have to do with the soil protection. Roots stabilize the soil, preventing erosion and maintaining fertility. Apart of the environmental benefits, trees provide important ecological benefits. In particular, biodiversity support is very important because vegetation provides food and shelter for a very high number of species, fostering rich ecosystems. Trees contribute to water cycle regulation. Plants help manage water flow, reduce runoff, and maintain groundwater levels. Also, trees contribute to nutrient cycling because natural vegetation plays a very important role in recycling nutrients like nitrogen and phosphorus. Apart of the environmental and ecological benefits, trees also provide important economic and practical benefits. In resources, forest and other vegetation offers timber, medicinal plants, fruits, fibers, etc. Agricultural productivity. Healthy vegetation improves soil quality and supports sustainable farming. Cost savings. The native plants often require less water, fertilizer or maintenance, and so we save money. Then we have very important social and health benefits. Trees contribute to mental well-being. Green spaces reduce stress, enhance mood, and promote physical activity. Also, trees contribute to air quality. Plants filter the pollutants, improve the air in the urban environment. Aesthetic value. Vegetation really beautifies the landscapes, increasing property values. And other benefits have to do also with social impacts. And trees have a very important social impact. We know now that the presence of trees increase property values, while as reported by, let's say, many scientists, city residents said that trees influence their decision about where to live. Also, studies have shown that trees can increase property values between 3 to 20%. Of course, vegetated space make the urban, let's say, areas much more attractive and have a very positive impact on moods. And also, we know that natural stimuli promote healing and recovery from stress. This is very important. Another important thing it is that patients which they saw trees from their windows in hospitals than a brick wall had shorter post-operative stays, fewer negative evaluative comments in nurse notes, fewer post-surgical complications, and fewer painkillers needed. So it helps very much really to recovery. Also, as I mentioned before, trees contribute really to improve mood. Scientific studies show that the reaction of humans to colorless lights of all rural and urban scenes, let's say, shown that people really reacted positively to, let's say, greenery. And this is measured by measuring the alpha waves, which are, let's say, released by the human, let's say, brain, and shows that people is happy. And we can really understand that when people are really, they are in contact with, let's say, nature and trees, they are much more happy because they release much more, let's say, alpha waves. Another study where really 120 humans, they seen a stressful movie and then show them one of 6 different videotapes of urban and natural scenes. They had really a much, let's say, positive, let's say, reaction to that. Now, let's start the impact and discuss about the impact of greenery on climate. Zones of urban greenery present much lower surface temperature than the opaque urban areas. For example, this is here, this part corresponds to urban greenery. You see that compared to, let's say, other opaque surfaces, temperature is to about 15 to 20 degrees of lower temperature. And of course, surface temperature. And of course, compared to black asphalt, there's a tremendous temperature difference. How much really greenery might decrease the soil, the surface temperature? Between 5 to 20, let's say, degrees. But this depends, of course, by the characteristics of the greenery. And mainly the color of the leaves, the climatic conditions, and the magnitude of the solar radiation, and of course, the ambient conditions in the water, let's say, in the vegetation. But the most important is that trees really, because of shading and a little bit because of the transpiration, helps and evaporation, helps really to reduce the soil temperature. How we really measure the impact of trees? To do that, we using very much, an index which is called NDVI, or the vegetation index. This is an index which measures this difference, providing a measure of vegetation density and condition. This NVDI, the NDVI, index, it's mainly, impacted by the fractional cover of the ground by vegetation, the vegetation density, and the vegetation greenness. So, and also indicates the photosynthetic capacity of the land cover. And we measure, the NDVI from the red and the near infrared reflectors in the red and also in the near infrared. And you see the formula. But what really I like that you keep in your mind is that NDVI is an index that shows really the fractional cover of the ground by vegetation, the vegetation density, and the vegetation greenness. High NDVI means really a lot of greenery. Low NDVI means less greenery. And of course, NDVI is directly, associated with the surface temperature. High NDVIs correspond to lower surface temperature. And you see, for example, the graph. The surface temperature is decreasing very much when NDVI, is higher. Affect the energy consumption of buildings. I will start from something very general. The National Academy of Science in the United States has really made, an announcement that the plantation of 100 million trees, combined with the implementation of light surfacing programs, could reduce electricity use by 50 billion kilowatt hours per year, which is almost 2% of the annual electricity used in the US, and at the same time reduce, the concentration of CO2 as much as 35 million tons per year. So trees may have an important impact on energy. Hello?
Speaker, please mute yourself. Others, please mute yourself. Sorry, sir.
No problem. At the same time, we know very well that shading by trees or mature trees can reduce the annual air conditioning use by 2 or 8% and the peak cooling demand by 2 or 10%. This is the magnitude of the contribution of the energy contribution of greenery. Studies about the impact of, trees and vegetation on the energy consumption. Studies have shown that planting in a strategic way trees, around buildings, and especially 3 trees around the home, this may cut summer air conditioning needs by about 50%. Of course, this depends on the type of house, the area, the climate, the type of trees, etc. But in average, we say that 3 trees out of your home means really an air conditioning. It gives the same impact like an air conditioning. At the same time, trees contribute a lot really to decrease the magnitude of the urban heat island and decrease the stored heat by the city and release water vapor, of course, transpiration through their leaves. Other studies show that by adding 1 tree per house, the cooling energy savings can be between 12 to 24%, while adding 3 trees, as I told you, is close to 50%. The direct effects of shading is 10 to 35%, and the remaining, let's say, savings are because of the evapotranspiration. So trees contribute really to decrease the energy consumption for cooling by 2 ways, because of shading and because of evapotranspiration. They transpirate water. The higher the, let's say, of the contribution, it has to do with the evapotranspiration. Shading, it contributes, but is not so important like, for example, evapotranspiration. Enough really evidence about the cooling power provided by trees. Yes, we have data from different, let's say, areas. For example, around the world, trees and green spaces create oases and decrease the nighttime temperature, for example, in Athens and in San Francisco by about, let's say, 8 degrees compared to the surrounding areas. But this is during the night. Some other, let's say, studies show that in Tokyo, in summer, the vegetated areas are about 1.6 degrees cooler than non-vegetated, let's say. Well, this is close to 2.5 degrees. In Mexico, they measure 2 to 3 degrees cooler respect to the boundaries. This is really the magnitude of, let's say, the decrease of the temperature inside parks. However, the knowledge we have is a little bit fragmented, and there are a lot of uncertainties. And there is a need, of course, to expand research on it. And we have really to understand better the gaps. But we have really to start organizing the whole discussion. And this is done by, let's say, introducing the idea of green infrastructure in the city. What is a green infrastructure in the city? According to the existing, let's say, definition, a green infrastructure is a network of natural and semi-natural green spaces, forests, parks, green roofs, and walls, which provide nature-based and cost-effective solutions. Also, if you like, another definition provided by the European Environmental Agency says and defines green infrastructure as a network of interconnected green futures that offer additional benefits and great resilience. So in general, we, let's say, refer to green infrastructure in cities and not just to trees or to greenery, green infrastructure. We have important benefits of green infrastructure. And because of this, there are very important, let's say, large projects all around the world to increase the green infrastructure in cities. We have huge projects, actually, Chicago, Los Angeles, New York, Sydney, Melbourne, and they like really to plant millions of trees. The impact, we will discuss about it. But before really starting discussing about numbers, and because numbers are a bit confusing, because you may have, let's say, a case study where greenery has really decreased the temperature during the day by 2 degrees or whatever, and another case study where really greenery has not decreased the temperature or even has increased the temperature. And this is a bit, let's say, confusing because people do not understand what really is the real impact of greenery. We have to follow another, let's say, more scientific, let's say, way. And this has to do with the understanding of the, let's say, physical operation of trees. As I told you before, trees provide cooling because of shading, something that everyone understands. Usually shading is not decreasing the temperature of the air, but it provides really thermal comfort. And also because of evapotranspiration. What is evapotranspiration? Evapotranspiration, according to the definitions, is a combined process through which water is transferred to the atmosphere from open water and ice surfaces bare soil and vegetation that makes up the Earth's surface really cooler. Evapotranspiration is composed by two, let's say, thermal processes. The so-called evaporation, which is the flow of water directly to the air from the sources, such as the soil and water bodies. For example, we have the soil, and the soil, because of the water content, evaporates. And because we have evaporation, we have release of latent heat, and this decreases the temperature. But also we have transpiration. What is transpiration? Transpiration is the flow of water from the root system through the plant and exit into the air as water vapor. So we have the water flowing from the roots through, let's say, the tree, goes to the leaves, and then it is, let's say, released as water vapor to the atmosphere. And this, let's say, exit occurs through the stomata of the plant. We'll come back and explain you which are the stomata. But transpiration is the release of water vapor by the trees to the atmosphere. This is very important. Which factors affect the evapotranspiration? Environmental factors. Temperature, humidity, solar radiation, many things. Plant crop factors, the type of plant, geographical factors, where we are in, let's say, a temperate climate, a cold climate, a tropical climate, and of course, soil-related factor, which is, let's say, the humidity of the soil. Let's see the different, let's say, factors which affect evapotranspiration, and at the end, define the potential of greenery. First, is temperature. The higher the temperature in a place, the higher the evapotranspiration. Because evapotranspiration depends very much on the temperature. When temperature is high, we have more evaporation and sometimes more transpiration, but not always. Humidity. Once we have very high humidity in an area, the evapotranspiration is low. Why the evapotranspiration is low? Because there is no potential for evaporation. If, for example, the atmosphere is saturated, it cannot really hold more evaporation, more water. In this case, there is no potential for evapotranspiration. You cannot add more water, in the atmosphere. Wind speed. When we have high wind speeds, usually this really increases the magnitude of evapotranspiration because it transfers, higher speed, transfer water vapor from the surface of the trees to the atmosphere. Of course, the moisture and the water availability. If we have less water available, we have less transpiration by the plants. How trees can really evaporate or affect, or have some transpiration if there are no water? Without water, we don't have really transpiration. This is something that has to be very well understood. This is not an automatic process that happens by the trees. Trees, in order really to offer to cooling, needs water. If you don't have water, they cannot walk. It's like a human body without blood. Solar radiation. Evapotranspiration is increasing with solar radiation because it increases temperature, and so we have much higher evaporation. Then, evapotranspiration depends very much, on factors related to the plant and the type of crop. The vegetative cover. If you have one single tree or you have really a forest, the degree of evapotranspiration is completely different. The shape and the size of the leaves. It's not the same to have a small leaf of any color with, let's say, a large green leaf of lower temperature. The type of the plant, how much really of sap of flow through, let's say, the tree. Also, soil factors. Do we have enough water in the ground? Evapotranspiration depends on the water table depth, the moisture of the soil, and the capillary characteristics. If you don't have water in the ground, and you don't provide irrigation, trees cannot really evapotranspirate. They don't have really the necessary resources to evapotranspirate. Then geographical factors, which affect very much evapotranspiration. Evapotranspiration is decreasing with latitude. We have much higher evapotranspiration in the tropics, much lower evapotranspiration in, let's say, the northern and colder climates. How evapotranspiration really happens? Excessive heat during heat waves affects very much the transpiration and the other physiological processes of plants, and this results in a very significant reduction of the latent heat release in the atmosphere. This has to do with the physiology of the trees. Like human bodies, they have a certain physiology, and we are affected by the heat. And we don't have the same operation when temperature is 25 or 45 or 55. The same happens with trees. Trees are very much affected by temperature. So, especially when we have high temperatures and low humidity, drought for example, the stomata, I mean the parts of the trees through which we have the evaporation and the transpiration, closes. And once they close, they don't have really flow of water through that, and it closes because they like to be protected. They don't like to lose their water during the high temperature. In this case, their surface temperature is increasing. And because their surface temperature is decreasing, and because they don't have enough water, trees may, let's say, may die, may, let's say, have important, let's say, problems of let's say, health, of plants' health. At the same time, once the temperature of the leaf is increasing, the sensible heat is increasing and it is released to the atmosphere. I remind you what we discussed the other days, that higher sensible heat means heating to the atmosphere. So trees, during the period of very high temperature and during the period where no water exists, they close their stomata, they stop evapotranspiration, and at the same time, because of this, their surface temperature perhaps it's higher than the ambient temperature because of the color of the leaves, and the sensible heat which is released by the trees may contribute to heating. This is something that we know very well, and during the very last years, we have observed in many parks, urban parks, during heat waves, where the temperature inside the parks is higher than the temperature outside the parks. And this happens because trees do not have enough water, but they are overheated, and so they release heat to the atmosphere. What is the solution? The solution is watering of the plants, and especially during heat waves. And once we provide, let's say, evaporation to the plants, in this case, plants and trees, they have the proper resources, and these resources really increases the flow of the sap through the tree, opens the stomata, and we have more transpiration. And many, let's say, studies, and you see some results there, show, for example, that once we have, let's say, watering and irrigation of the trees, their sap is increasing really considerably. As I mentioned to you, during the heat waves, the stomata are tiny parts of the leaves, close and stops really to evaporate water. This happens for almost, let's say, 95% of the trees, but not for all trees, because there are some trees which are really very tolerant to the heat. And in this case, these trees really may contribute to evapotranspiration and to urban cooling for higher temperatures. However, above 40 degrees, which is the upper, let's say, threshold, stomata close almost everywhere. And the transpiration, let's say, rate is minimized. So if trees are not irrigated and the temperature is higher than 40 degrees, don't expect really any cooling from, let's say, the trees are part of the shading. And we have now, during the last 10 years, there are a lot of experiments, and much better knowledge about the sensitivity of the different families of trees to extreme heat and drought. So we know now which really trees and which, let's say, families of greenery, they have a very high efficiency, they are more tolerant, and how really they react. So we have databases that provide information to those they wish really to use it about, let's say, the heat tolerance of the trees. But although we know, let's say, that this happens, we know that trees above a certain temperature really stop their evapotranspiration. We continue research to understand how much of evapotranspiration is lost. In, let's say, the graph here, you see the results that we collected 2 years ago with my PhD student about, let's say, the evapotranspiration of eucalyptus in Australia. You see that above a certain temperature, and in this case 30 degrees, the evapotranspiration by the eucalyptus decreased considerably. And in general, you know, the threshold temperature above which the evapotranspiration starts really to decrease is between 30 to 35 degrees, depending on the type of the plant. But this happens for non-irrigated trees. Same results coming, you know, from other parts of the world. For example, in the graph here, you see the variation of evapotranspiration above a certain temperature in Africa. And you see, for example, how much the evapotranspiration is decreasing above a certain temperature. It's not the same decrease for all trees, for all climates. But what is important is that it decreases. And above, let's say, 40 degrees, it's minimized. All trees have the same performance? All trees, they have the same impact? No. Plants with deep rooting system can collect water from deep in the soil, and so they may have a higher transpiration rate. So trees with deep roots, really, or a deep rooting system, have a better performance. On the contrary, plants with shallow rooting systems cannot really collect water. And in this case, the mitigation potential of, let's say, shallow trees is very limited. On the other hand, once we diversify the cooling potential and the evapotranspiration potential of different type of greenery, we have to understand that trees have a much higher evapotranspiration than, let's say, the grass or the shrubs. Why? Because trees have a deeper root system, so they can collect water, you know, from the ground. The canopy of trees is cooler than grass because you have a canopy. The water lost through evapotranspiration is accumulated around the greenery. This is around the canopy. This is not really the case of grass. The soil with trees have more organic substances, which increase the penetration potential and the absorption potential of the soil. So you have more water. So there is a tremendous difference between the cooling potential of trees and the cooling potential of grass and shrubs. This temperature, this difference in water capacity between the trees and the low vegetation, you know, especially grass and shrubs, they may result in very important opposite effect in the urban climate. For example, an experiment, large-scale experiment that has happened in California, in Los Angeles, where they wanted really to test the use of drought-tolerant shrubs without additional irrigation. And they wanted really to use these, let's say, plants in order to decrease the temperature because of the lack of water, has resulted in a daytime temperature increase by 1.9 degrees. So they planted, let's say, non-irrigated shrubs in Los Angeles, and in these areas, and this was a very large experiment, temperature increased by 1.9 degrees. Why? For the reasons I explained you before. No water, evapotranspiration, closed stomata, more sensible heat, overheating in the city. This is not the case during the night. During the night, we have a cooling, even if you don't have, let's say, water. The nighttime cooling is really because of the modification of the soil thermal properties by replacing vegetation. So during the night, because you don't have a very high evaporation from the soil, you don't have solar radiation, there is more water availability, there's a higher water availability that helps really trees to get some water from the soil and have some evaporation. So it is very important to understand that trees, they have a completely different cooling potential during the day and during the night. The other thing which is very important is that during heat waves, there is a very common phenomena that refers to the daily pattern of evapotranspiration by the plants. We have a very sudden fall in the morning. So in the morning, you may have during heat waves a very low, if you have, evapotranspiration rate. And this is because of the physiological process of the plant, which really fail because of the high temperature to find, let's say, inadequate water supply. This is very common in areas with high temperatures and, let's say, low humidity and drought. This is very common, you know, in dry and desert climates. So trees there, even if you plant a lot of them, they may not contribute, especially in the water at all. As I mentioned to you, to avoid this problem, you need to have trees which really can capture the water from the soil. And this means deeper roots. And these trees have much, let's say, better tolerance. But we have to understand that these trees needs about 20 to 25 years really to get the proper size and also to provide evapotranspiration. So don't expect that small trees without deep rooting systems can really contribute immediately. You need 15 to 25 years to have this. On the other hand, the canopies of the trees play a very important role because they can buffer in an effective way the extremes and they can mitigate climatic change. Drought, which is predicted to become, of course, more frequent in the future, may alter the microclimatic cooling potential of trees. The canopy temperature regulation, it is really investigated by many, let's say, people, and once really we compare the, let's say, the canopy temperature regulation by 5 different, let's say, different mature tree species, we've seen that it is completely different and depends on the trees, let's say, characteristics. And from the graph, you can see that evapotranspiration by different type of trees in different kind of canopies may, let's say, differ by a factor of 3. So it's not only the type of the tree, it's not only the, let's say, the characteristics of one tree, it is also the characteristics of the canopy. Trees behave completely different when they are together or when they are alone. There is a very nice, let's say, book that is published a year ago that has compared, for example, the growth and the contribution of one tree planted, you know, in a forest together with other trees, And the same tree planted in, let's say, an urban climate, an urban environment, alone, the size and the growth and the contribution of the tree really in the forest was 3 times higher. And this because, according to certain theories, trees, they have a social life. They don't like to be alone. They like really to communicate with the other trees. And how this happened? This happened through their rooting systems. This happened through, let's say, the emission of BVOCs. There is another system which, the physiologists, they call it soil wide web or wood wide web, WW web. And this is really a system of transmission of information in the soil between, let's say, the trees, very slow because, the life of trees is much higher than the life of human beings, but they transmit information and they communicate between them and they have a social life and they have their own way really of, let's say, of social life and in general, let's say, of growth. This is very important, and the very recent years, we learn a lot about, let's say, the physiological life of trees, and now we can really take into account, because for many years, many people, in a silly way, they believe that by planting trees, you are saving the problem. No, you have to respect the trees. The trees, they have their own life. They have their own physiology. They have their own, let's say, needs. There is a lot of really research on, let's say, the cooling potential of trees, and especially the direct and the indirect effects of meteorological factors, and how trees really affect the latent heat, and how really this contributes to, let's say, the cooling of the city. The decrease of the latent heat, which decreases the temperature in the city, it is because of the decrease of the subflow, and this really creates an important problem, especially for isolated alone trees. In canopies, because of the transport of, let's say, water between the trees, you may not believe it, but once one tree sends the message to the others that let's say, I don't have enough water and I'm under risk, the other trees contribute and send water to them through the rooting system. So trees, in canopies, they have a much better performance, a better evapotranspiration, a better cooling potential. Do we have enough really measurements and do we have enough knowledge about it? Yes. I'd like to show you some results from, let's say, LA, how really irrigated and not irrigated, let's say, greenery has, let's say, released sensible and latent heat. In the lower part, in the upper part, you see the, let's say, non-irrigated trees, exactly the same trees. You see that the latent flux, blue, is almost nothing. Once they started really to irrigate the trees, the latent heat has increased tremendously, contributing to cooling, because latent heat is cooling. Sensible heat, heating in the atmosphere. When trees were really non-irrigated, the sensible heat, the red part, was very high. Trees really increased the temperature in the city. On the contrary, once really they start irrigated, this has decreased tremendously. So we have enough evidence about the heat and thermal impact of irrigation. I'd like to show you some other, let's say, data from Melbourne. These are experimental data. Increase of the irrigation as a function of the, let's say, diurnal cooling of greenery. You see, for example, that once we have continuous or during the daytime or just the nighttime, irrigation, the increase of the irrigation has almost a linear impact on the cooling potential of trees. And you see the differences. While, let's say, in non-irrigated, almost or very low irrigated greenery, had a cooling potential of 0.5 degrees, once we increase the irrigation, this was 2.2. So the irrigation helps a lot to evapotranspirate, decrease the temperature, but the amount of irrigation also defines the degree of released latent heat. On the other hand, it is very important to understand that because of the shading, the soil temperature behind the canopy or behind the trees is really much lower. And we have, through satellites, measurements all around the world, and I'd like to show you some data from, Europe, where we measure the surface temperature difference between, let's say, covered by trees canopies and soil and non-covered by trees soil. You see that for most of the places, we have a much, let's say, lower surface temperature under the canopies. In the northern climate, the decrease of the temperature may be as high as 10 degrees. In southern climates that we have much higher solar radiation, much higher, let's say, temperature, this temperature difference may be 0 to 4 degrees. In places with extreme heat and also with very high solar radiation, unfortunately, trees may contribute to heating. And you see, for example, in Gaziantep, which is in Turkey, the temperature, of the soil behind the trees was higher. Why? Because really trees cannot really help to provide enough shading and enough really protection of the soil. So everything is relative. Even evapotranspiration and shading may really contribute to cooling, but if it's not done in a professional and scientific way, may contribute really to heating. And the mean summertime temperature differences between the urban vegetated areas and the continuous urban fabric, the city, once it is plotted against evapotranspiration of vegetated areas, it shows really these results. You see that the higher the evapotranspiration, the higher the evapotranspiration, the higher the temperature difference. So if really you have well-operating plants and trees, if really the plants are healthy, if they are well irrigated, may completely contribute to decrease the soil temperature and provide comfort. If really the evapotranspiration is low, the cooling potential is close to zero. So remember that. What about the impact of urban parks? We know that urban parks, and you see the, let's say, Central Park in New York here, urban parks provide very significant climatic benefits. And of course, we have a complete and important decrease of the temperature and decrease of the temperature around the park, but at the same time may offer important social impacts. They, let's say, enhance human well-being. They decrease the pollution levels. They contribute to better public health. They increase the poverty, the higher property, let's say, values. We have already discussed about this, and of course, we have a better aesthetics. During the daytime, urban parks maintain lower ambient temperature compared to, let's say, the built areas. Why? Because you have evapotranspiration and because you have shading, except during the period of very high temperature. At night, they remain cooler because of the great irradiative cooling potential. They irradiate a lot. And so they reduce the sensible heat, and which results from the lower daytime heat storage. In parks, you don't have heat storage. In the city, because of the mass, because of the asphalt, because of the, let's say, concrete, you have a lot of storage. This stored energy, it is released during the night. In parks, you don't have that because you don't have storage. So the temperature during the night in parks is much, much lower than the temperature in the surrounding area. So the main, let's say, contribution of urban parks is during the night. I'm not saying that it's not during the day, but the contribution is much, much higher than, let's say, during the night than during the day. All urban parks contribute the same way? Not at all. There are different factors that define the cooling potential of a park. First, the structure and the size of the park, the sky obstruction, the type of plants used, the irrigation frequency, the characteristics of the surrounding urban zones, and I will explain you what does it mean. How much of heat emissions you have around the park, the density, and many other things. And of course, the climate in the region. In order to, let's say, quantify the cooling potential of trees, we have defined, let's say, a parameter which is called the surface park cooling intensity, which is the difference between the average temperature, land temperature, soil temperature of the urban fabric, and also around the park, and also, the temperature in the park. Is the temperature difference, the soil temperature difference between the park and the surrounding area. And so we can measure this, and we can see how much really the park has decreased the soil temperature. And you see, for example, some measurements from several parks really in Athens. You see that the green parts shows really that inside the parks, the temperature difference, the soil temperature difference is very high. But this temperature difference is extended up to 100, 200 meters beyond the boundaries of the parks. So the parks contribute to decrease the soil temperature, inside the boundaries, but also a bit outside of the boundaries. And measurements of this, let's say, parameter, also in the same park in Athens, show that by increasing the park size up to 20 hectares, you don't have any additional benefits. Because it is very important to understand which is the optimum size, in a city. There is an asymptotic increase of the cooling potential, and you see there, and of the parameter defining the temperature difference as a function of size. Above a certain size, 20 hectares, you don't have any additional benefits. So if really we try to design, let's say, parks or additional greenery in a city, instead of having a huge park, it's much better to have smaller parks distributed in the city, because each one of these parks contribute in the surrounding area, and so you cover a much higher part of the city. Instead of having huge, big parks, it's better to have distributed parks really across and along the cities. Also, let's say the perimeter of the park, and also the surface of the park. The ratio of the park perimeter to the park area, P to A, really defines the cooling potential. The higher, let's say, the ratio of the perimeter to the area shows a lower contribution to cooling. So it is very important to optimize the size, and the perimeter of the park and the area of the park defines really the cooling potential of the park. At the same time, we have defined another parameter, which is the temperature difference, the ambient temperature difference between the park and the surrounding area. Not the soil temperature difference that I presented you before. How much a park contributes to cool air around its boundaries or out of its boundaries? In general, the rule is that the magnitude of the park's influence, of course, depends on the size of the park, and its impact is limited to roughly one park width. So if the width of the park is 500 meters, you may expect a decrease of the temperature 500 meters out of the boundaries of the park. This is very general, maybe lower, maybe higher. Generally, it's really much lower. All measurements we have from different, let's say, parks show that this, let's say, impact and influence of parks in the surrounding area, it is limited between 200 and 400 meters. But this is not something very general. Depends on what is happening around the park. The very first time that I measured really the performance of the park, and that time I was in Greece, it was in the so-called National Park of Athens. This is, let's say, this is a park in the very central area of Athens, which is surrounded really by many very important, let's say, streets with a lot of, let's say, circulation and a lot of traffic and a lot of anthropogenic heat. So we measure what is happening now, the temperature inside the park, and the temperature was really much lower than when we expected in the city. Once we exit from, let's say, the main door of the park, the main gate of the park, and we enter, to the street, 5 meters from the gate of the park, the temperature increased by 5 degrees. Why? Because of the generation of the anthropogenic heat. It was like you put fire around the park. In this case, because of the very high temperature of the air around the park, the coolness of the park cannot really escape, cannot really go away, and cannot really penetrate inside the city and cool down, the city. So it is of extreme importance to understand and really to design parks, take into account all these parameters. First, which is really the gradient of, let's say, the cooling potential of trees. We say that is 0.33 degrees per 100 meters. And this is something really that is the average value. So, but depends very much on the conditions. And average value, of course, gives you an order of magnitude, but depends very much on the specific characteristics of the park. And during the night, when, as we have already mentioned, the cooling potential of the park is much higher, this is because of the very high radiation, as I mentioned to you, because of the minimum or minimized heat storage, and also because we have, let's say, more wind in the park than the surrounding areas, because let's say, the urban areas, you have less wind because of the obstacles by the buildings. There is a very strong correlation between, let's say, the temperature difference between the park and, let's say, the penetration of the coolness in the city. And this depends very much on the characteristics and the density and really the characteristics of the park, but also of the surrounding area. And the daily amplitude between the night and the day, let's say, temperature in the park also is defined by the characteristics of the surrounding area and also of the park. So a park is not really contributing to decrease the temperature in the city in a general way. This is not a rule. A park may contribute almost a minimum, let's say, cool energy if around the park we have a lot of heat, a lot of anthropogenic heat, a lot of, let's say, high-rise buildings that are not allowed really the air to penetrate, a lot of stored heat, materials that really have a very high temperature. So in this case, we reduce the help and the contribution of the trees. And this is very clear once we measure really the penetration of coolness in different, let's say, parts of the trees. If we measure the coolness of let's say, the penetration of coolness in, let's say, out of a park, the same park, towards, a direction which there are no important anthropogenic heat, no high density, we may see that during, let's say, in this area and across this area, we have a much higher penetration. Once we go for the same tree and measure in another direction where we have more anthropogenic heat and we have, let's say, high-rise buildings, it's completely different. So trees really depend on the climatic conditions as a whole. So when we design really in a city, we consider not only the characteristics of the trees, but we consider the characteristics of the whole city. And there are important studies really that shows that the contribution of trees in the urban climate is really completely different to different cities and different climatic conditions. And the temperature decrease, for example, may contribute to, let's say, decrease the ambient temperature by, in some cases, the worst cases, 1%, in some other cases, up to 30 or 40%. So do we have a rule really to understand how really a park may contribute to cooling? Yes. Now we can say that in general, by increasing the green infrastructure in a city, we can predict the temperature decrease during noontime, 3 o'clock in the afternoon, as a function of the initial green infrastructure or initial fraction of green infrastructure to the final fraction of green infrastructure. Imagine, for example, that you have a city that the green infrastructure, it is 15%, for example, at the beginning, the initial one, and it, after, some interventions, this 15% goes to 20, 25%. In this case, we can use, this temperature, this formula here, which shows that the expected temperature decrease because of the, let's say, additional greenery is a function of two parameters plus really the parameters that define the initial and the final, let's say, green infrastructure. So we have, let's say, a kind of, an index, a kind of a recipe that can give you an approximate what really happens. And this is what really you can expect to have. From all the, let's say, measured and reported, let's say, measurements around the world about greenery, we know, for example, that during the day, increase of the green infrastructure may contribute up to 1 degree of temperature decrease. You see, for example, these are data from existing parks all around the world. If I'm not wrong, this is from 50 different parks. And you see that during the day, even if you increase, let's say, the green infrastructure up to 60%, don't expect that at the city level, the decrease of the temperature will be higher than 1 degree. It is really much different during the night. I already mentioned to you that cooling of trees is much higher during the night. The contribution may be up to 2 degrees. So it is very important really to have all this information and calculate from the previous formula the expected decrease of the temperature during the day, but also you can calculate the expected decrease of the temperature during the night by, let's say, another formula. So you have some useful, let's say, tools that can really help you to understand in average what can be, let's say, taken by, let's say, can be given by, let's say, greenery. I will stop for 5 minutes here. If you have questions, please ask me now, and then we may continue.
People, you can either write in the, okay, fine. There is a question from Dr. Faiz Ahmed, which says, which criteria should guide species selection for maximum canopy cooling? Whether it is leaf area index, albedo, transpiration rate, or drought resistance?
All of them. All of them. You cannot really, let's say, neglect some of these parameters. First, the most important is to take into account the climatic parameters in the city. If you design, for example, for a tropical city, or if you design, for example, for a temperate city, the potential of the trees will be different. The tree spaces depends also on the, let's say, the characteristics of the trees, the availability of the water, and the climatic conditions. In a humid climate, you have completely different, let's say, options than in a dry climate. Then, the overheating at the city scale, which is the impact? What is happening really regarding anthropogenic heat and convective heat? What is happening around, let's say, the radiative, let's say, losses? Fourth, very important, let's say, the type of trees and especially the rooting system. We don't have the same rooting systems everywhere. And we have native plants that some of them, they have a very deep rooting system, some others no. So you can't find a general formula that really tells you what to do. You have to know the science behind it. It's complex. You have to take into account all these parameters. You cannot make it in a simplistic way. If you do it in a simplistic way, you will not have results. So you need to have scientific knowledge and take all these parameters into account. It's not easy, I understand. It's difficult. But this is the only way to be done, to be successful.
Do you have any other questions? Well, let us first accept that there is no general rule that more trees means cooling.
It's not so simple. While yesterday, when we discussed about materials, things were a little bit more, let's say, smooth and simple how to do it. In greenery, it's very complicated. It's very complicated, but it is a very efficient mitigation technology and system. And we need really to understand it. And we need really to know the science behind it. From the very beginning, I have repeated so many times that heat mitigation is a science. It's not something which is empirical. You can't do it without the proper scientific knowledge. So if you are interested to work on heat mitigation, if you wish really to intervene, design, and contribute to decrease the temperature in your city, you need to have the proper scientific knowledge. Without it, you will make huge mistakes.
Right. So basically, you're saying we need to unlearn first.
And this is the reason that these courses helps a lot. Of course, I understand that in 2 hours lecture, you cannot absorb everything and you cannot be an expert. But it is very important that you get the message. And the message is that you have to study. You have to improve your knowledge. You have to become an expert. If you don't become an expert, don't do it. You can't really be a medical doctor and operate people. You read newspapers. You have to make studies. 7 years in the medical school. And I don't know how many years of experience. The same is with climatic science.
Right. Already we are humbled. Now we are nowhere. That's what we have come to. If no other queries, which is understandable to me, because I don't know where to start from, because I don't know anything already. No queries. Okay. We are not having any questions, Professor, at this stage.
Okay. Let's continue. So let's go and present some case studies. I have already mentioned to you the second day the performance of greenery in Riyadh. And I recall you that the whole study have shown that when really we try to use greenery without proper irrigation in Riyadh, a dry atmosphere, then greenery contributes to heating. And this is very important message. I will tell you a small story. In Riyadh, they designed a huge park, huge, the biggest in the world, in the center of the city. And they have brought some, let's say, experts from a very big country, I don't mention this, which promise really that they will decrease the temperature, promise to the king, they will decrease the temperature by 10 degrees in Riyadh. And when, I started working as a consultant there, and I met them, and also the minister really intervened, and we discussed about this program. A very arrogant American told me, I will decrease the temperature by 10 degrees, very simple. And I asked him, have you promised this to the king here? Yes. Okay. Just promise that you will decrease the temperature by 1 degree, not 10 degrees. He said, no, we know it. Yeah. And when really I, let's say, presented them, the actual, let's say, knowledge, then he came to me and said, you saved my life, because you are under risk there if you promise 10 degrees and you have 1. So don't promise and don't believe on myths. Believe only on science. And don't believe all those that they are coming and saying, let's plant 5 million trees, let's plant 10 million trees. The result may disappoint you, and we will come back to this. Also, if you remember, I told you that the cooling, let's say, potential of trees in Riyadh changes completely once really we are using irrigated trees. And this is one major condition. I don't think that you have to make special studies to understand this. Never forget that without irrigation, trees do not really contribute. It's like to have people asking them to walk without feeding them. If they don't have food, they cannot walk. Trees without irrigation, they cannot contribute. Some other, let's say, studies that we have performed together with my friends from Calcutta, from the city of Athens. Athens is a dry climate, but it's not Riyadh. Humidity is much higher. Showing that really well-irrigated trees at the city scale may decrease the temperature during the day up to 1 degree once we increase, the infrastructure, the green infrastructure by 70%. If we can decrease in a magic way the green infrastructure by 30% in Athens, the contribution of the green infrastructure will be 0.7 degrees. This is really at the city scale. This is really what we expect at the city scale. The temperature decrease, and you see here the temperature decrease, depends very much on the size of the trees, on the size of the parks, on the landscape, let's say, design, and many other things. But don't expect more, let's say, than 1 degree, the maximum. During the night, you may have a decrease of the temperature up to 2 degrees. Another important study that we have performed also with the contribution of our colleagues from Calcutta, it is for Dubai. And also we have found there that under the climatic conditions of Dubai, we may, let's say, by, let's say, 1.5 degrees during the day, 1.4 degrees, but this means that we have to increase the infrastructure, the green infrastructure, by 75%. 75% is too much. And of course, the water has to be, the greenery has to be well irrigated. Just to recall you that actually, in Qatar, they have a plan to plant, I think, 2 million trees, you know. The main problem will be, let's say that they need a lot of water, but this will increase tremendously humidity because it's a humid climate. You may have, let's say, a little bit of temperature decrease, 1 degree, but a tremendous increase of humidity. And this will decrease the levels of thermal comfort, because thermal comfort is not just a function of temperature, it's also a function of humidity. So once really we, let's say, design major let's say, implementations of mitigation technologies, it's not only the temperature that has to be taken. We have to consider all the parameters that define thermal comfort, and especially, you know, humidity, because greenery, if it is irrigated, will increase very much the humidity levels. Another important study that we have done in Melbourne, in Australia, we have really shown that by increasing the green infrastructure by, let's say, 35% or even 50%, we may achieve a temperature reduction on the city scale up to 0.8 degrees. Why am I repeating this data? Because you have to understand that with greenery at the city scale, don't expect to have a tremendous, really, contribution to temperature decrease. 1 degree during the day is perhaps the maximum you can, let's say, achieve. Is it low? No, it is not low. It is not low. It is very important. But I read, you know, many reports here and there by semi-informed or semi-knowledge people that they say, plant trees and temperature is decreasing by 10 degrees. If you, let's say, just go through LinkedIn, for example, you have some empirical people that they say green infrastructure decrease temperature by 10 degrees. No, under the tree, not at the city scale. So it is very important, really, to understand the real impact. At the same time, it is very important to understand how much really greenery contributes the whole year. And this can be done by counting the cooling degree hours. For example, may decrease because of the use of greenery. And I'd like to show you what is happening. A warm climate is, let's say, moderate, it's a temperate climate. Once really we increase the green infrastructure by 35%, which is very difficult because there's no space, you know, cooling degree hours may decrease, you know, from 143 down to 135. This is, or 126. This is a very modest, let's say, decrease. But it is important because it provides comfort and helps, and also aesthetics. The same, you know, results are taken for a similar study performed, you know, for Western Sydney. As we discussed yesterday, Western Sydney is the, you know, the warmer part of the city and the poorest part of the city. The government here in Australia had an initial plan to, let's say, plant 5 million trees. The study, they have asked us to perform the study for them. In reality, even if you have 2 million trees or 5 million trees, the cooling potential is exactly the same because there is saturation. Even by planting 5 million trees, the expected decrease of the temperature is 1 degree. Maximum, let's say, temperature reduction can be 1.5 degrees. But to achieve such, you know, a result, you need to spend 10 to 27 liters of water per day for each tree. And this means, you know, million liters of water per day. This means an increase of the water consumption in Sydney by 35%. If we are ready to do it, we can do it. If we have the, let's say, the water to do it, if we can use wastewater, if we can use any type of water, yes, it is worth to do it. But don't forget that we need to increase tremendously the water, let's say, contribution. Similar results also regarding, the increase of the evapotranspiration. What does it mean this? That we combine additional trees with water bodies. And we have much higher evapotranspiration, not only because of the trees, but also because of the water. In this case, we may increase the cooling contribution up to 1.5 degrees. And once really we have 2 million, let's say, additional trees with non-irrigated green roofs, which is really a technology that is very common, mainly, in rich countries, because it's very expensive technology, then in this case, we may, let's say, achieve the maximum in some parts, a decrease of the temperature by 2 degrees. But in this case, the additional consumption of water is huge. And once really we're using irrigated green roofs, plus really 2 million trees, in this case, we, let's say, have almost the same potential around, 1.5 degrees. During the night, may have, 2 degrees or 2.6 degrees. But in this case, the water consumption is really tremendous. Where really green, let's say, infrastructure helps more? We have performed together with our colleagues from, let's say, Calcutta, studies from Malaysia, Kuala Lumpur. And we have really tried to see the potential of an additional greener infrastructure of 30 or 60% of non-irrigated vegetation. Why non-irrigated vegetation? Because it's a humid climate. And we found really that by increasing the green infrastructure by 30%, the maximum really decrease of the temperature at the city level is 0.9 degrees. When we increase the green infrastructure by 60%, almost impossible, we may have, let's say, a contribution close to 1.5 degrees. And I mentioned before green roofs. Green roofs, is a new, let's say, tendency a la mode, as we say, all around the world, but mainly in the rich country because the cost is very high. And green roofs, they have, let's say, several benefits. They provide mitigation, energy conservation, stormwater runoff management, improve air quality, enhance durability of roofing materials, and many, many other things. Do we have enough knowledge about the cooling potential of green roofs? Yes. Green roofs may contribute to decrease the temperature, and the most important is that they decrease the temperature of the air above the green roof, which makes, let's say, the air a little bit, let's say, heavier, and in this case, helps really to create a secondary circulation of air in the city, and this helps a lot. But mainly contributes also to decrease very much, really, the pollution, let's say, load in the city. Which is the expected energy conservation from the green roofs? Depends. We have reports from 1% to 40% for the specific buildings. And the expected really decrease of the temperature at the city scale may be of the order of magnitude between 0.3 to 0.6 degrees. There are cities that they are promoting very much green roofs. For example, Stuttgart in Germany, they contribute, they, let's say, pay the, let's say, the citizens to install green roofs, and the state is contributed a very high amount of money to do that. Of course, this is not really a warm climate. This is a temperate climate, and this may help really a bit to mitigate heat, because overheating there is not really so important, and humidity also is not really so high like in the tropical climates. What about, let's say, the performance of the different type of greenery in green roofs, especially green roofs, which is not temperate, it's warm, but it's not so warm. For example, the, let's say, climate of Athens. During heat waves, green roofs may contribute to decreased temperature up to, let's say, 0.3, 0.4 degrees at the city level. At the rooftop surface, the soil, or the surface, the temperature of the green roof may decrease up to 2.7 degrees, up to 7 degrees. And this is very pleasant for those really that they live there. But at the city scale, the contribution is really very moderate. We have another important study that we performed for Seoul in Korea, which shows really that by increasing the, let's say, the cover of green roofs or the fraction of green roofs at the city level up to 90%, for example, most of the buildings, they have a green roof, we may expect a decrease of the temperature up to 0.54 degrees. And this is published in Nature Journal, which means that really 90% of the buildings having a green roof may contribute to decrease the temperature by 0.4. And let's say the surface temperature up to almost 2 degrees. It is not really something negligible. It is important, but this is the real, let's say, threshold value. This is the real limit. And this may contribute to decrease the energy consumption of the buildings. The direct impact of green roofs on the building, let's say, energy consumption is important because it decreases the flow of heat. And also, it helps really to keep the buildings cooler. In this case, we may, let's say, have a benefit close to 1 kilowatt hour per square meter in Seoul. 1 kilowatt hour per square meter is high or low, depends where you are. For example, the average cooling demand here in Sydney is close, let's say, to 60 or 70 kilowatt hours per square meter. In Mumbai, it's much, much higher. It's 140, 150. So 1 kilowatt hour per square meter. This is really the contribution, of course, for well-insulated buildings and really for well, let's say, maintained buildings. And I like really to proceed on the energy consumption and the energy impact of greenery. The results we have really from different parts of the world depends on, let's say, the characteristics and the boundary conditions of the study. So we have results showing that the increase, of urban infrastructure, of green infrastructure in cities may contribute between 2% to 90% less energy use, which means that the whole spectrum is there. And this really validates what I told you before, depends on the characteristics and the way that is implemented. At the same time, the result shows that also the use of greenery may decrease the heating energy consumption between 1 to 20%, mainly because of the wind effects. We really stop the wind. And the analysis of 40, let's say, different important and large implementations of greenery in the world has really concluded to something which is important and you can really take into account. And the first one, it has to do with the evaporation. The evaporation from trees is 3 times more effective than the cooling provided by tree shading. We have already repeated that. Some studies, they show that shading contributes to 10%. Some others, they say that it contributes to 30%. In general, evaporation is 3 times more important than shading. The density of the green spaces around buildings is very important on the energy consumption. How much of green spaces you have around and how this is distributed. The lawns, the turf, may provide some cooling, but high water consumption for irrigation is a major drawback. For, let's say, turf and lawn, the cooling potential is not negligible, but you need to have a lot of water. Also, Trees reduces wind speed, and this really diminishes the cooling benefits. The impact can be minimized. To optimize cooling, trees should be planted at a distance from a building to allow air circulation indoors. You don't have to block the wind and the ventilation because of the trees. Of course, this may compromise shading. Then, trees which are planted on the west side of buildings offer the most effective shade and provide 3 times more cooling savings compared to the other orientation. So we know the trees which are planted in the west part of the cities, they have the better, let's say, contribution. Also, medium-sized trees planted 9 to 10 meters away from the western side of the building, as well as large trees 9 to 15 meters away from the building, can offer sufficient shade while minimizing potential structural impact. 9 to 10 meters away from the trees. Now, deciduous or evergreen trees planted on the east and south sides also can contribute to cooling, but this is not very recommended except in very hot climate with short, mild winters, because they can block solar radiation in winter. We don't like to block solar radiation in winter because this is increasing the heating demand. Once we use trees as windbreaks, we can decrease the heating demand, especially in cold climates. The way that we place the trees around the buildings has to be optimized in order really. This means that we have to balance the heating and the cooling benefits when really we decide to plant trees, around buildings. Heating penalties is found to be highest when conifers and evergreens, let's say, are planted on the south facade in cold climates with long severe winters, because they block solar radiation. To maximize cooling while avoiding heating penalties, we have to use deciduous trees because they reduce solar radiation by 35 to 50%. So deciduous trees in this type of climate may provide, let's say, cooling during the summer and not really increase the heating demand. In the northern hemisphere, where India is, trees planted on the north side of buildings have been found to increase electricity use by 1.5% in California, while these planted in the west and south side may reduce demand by 5%. So the way that you plant trees and where you plant trees plays a very important role on the energy consumption. Trees which are planted around low-rise buildings, of course, provide greater cooling benefits than those around high-rise buildings because the impact it's clear that it's much higher. Now, how much of cooling benefits we have? This depends very much on the density and the foliage of the planting patterns. We have much higher cooling effects when really we have a continuous canopy of shade, and specifically when the leaf area density is close to 2.5 meters per cubic meter. So this is, of course, a rule of thumb. What about greenery and air quality? We know and we accept that by expanding urban green infrastructure, we have better human health. And this happens because of different mechanisms. Because we reduce ambient temperature and moderate extreme heat events, we lower urban pollutants concentration, we provide space for social activity and interaction, and of course, we offer psychological and aesthetic benefits. There are a lot of studies which really examine the impact of green infrastructure on mental and overall human health. And it is found that really green infrastructure helps really to decrease heat-related mortality and also improve mental health. And of course, this has to do with several mechanisms: psychological and observational benefits, environmental benefits, better physical activity, enhance social interaction, and so on and so on. There are many studies, mainly done by epidemiologists, which shows, for example, that in green areas, let's say diabetes or cancer, it's much lower than in areas with lower greenery. I have serious doubts about these studies. Why? Because it's not greenery that really defines the, let's say, diabetes in an area. There are so many other parameters. For example, those that live in highly vegetated areas in a city usually is the rich people. Rich people have, other kind of habitudes than poor people. They don't smoke, they have, let's say, better food, and they have many other benefits. So the decrease of diabetes in the green areas is not because of, let's say, the presence of the trees. That may help. It's because of many other parameters. So we know that really greens contributes a lot to have better health, but in the name of God, it's not just green that really helps. There are so many other parameters that have to be taken into account. We have many reports and papers that shows how much really greenery decrease really the, let's say, mortality. For example, in Rome, they say that, for example, decreases 4 deaths per day. Or in Madrid, we had, let's say, 1 death per day, or in London, 2 deaths per day. Okay, yeah, that's fine. But this depends really on the overall climatic conditions. Studies are performed in non-polluting city with zone, etc. Yeah, greenery may contribute, but in a very polluted city with a tremendous really load of pollution, with very high temperatures, greenery may contribute, but we have really to take a distance from all these studies and really consider the, let's say, specific conditions. However, actually, take into account all the existing studies associating heat-related mortality against green infrastructure. We know, for example, that you can see from this graph, I'm sorry, just move it, that the drop of the daily maximum temperature really decreased the rate of the heat-related mortality. So if, for example, we succeed to decrease the temperature in a city by 1 degree, we may have a decrease of the heat-related mortality by 28%. This is average, of course. And this is based on real data from all around the world. In another city, you may have, let's say, plus, minus something. But this gives the order of magnitude and an average value that helps really to understand that greenery really has a tremendous impact on health. And there is some formulas that I showed you before, really, that shows really how greenery helps. And the reasons behind this help of the, let's say, of greenery related on the decrease of the heat-related mortality, mainly it has to do with the decrease of the ozone concentration. In reality, greenery decreases the pollution concentration. And this, of course, has a very important impact on heat-related mortality. But during, let's say, extreme heat periods, when the cooling effectiveness of greenery is really low, we may, let's say, have an increase of the temperature 5 degrees because, of the, let's say, the increase of the temperature. And in this case, we may have, let's say, an important increase of the ozone. Why? Because, unfortunately, greenery, when it is under stress, emits or releases some chemicals which really are called BVOCs, biogenic volatile organic compounds. These BVOCs are 3 to 5 times more toxic than the exhaust of the cars. And this is the way that trees really are trying to be protected from the insects and protected, from human beings and everything. So although greenery in general contributes very much to decrease really pollution in a city, during the period of high temperatures, non-irrigated trees, unfortunately, emits, let's say, BVOCs. And BVOCs really increase the concentration of ozone. Under normal conditions, greenery contributes really eliminate ozone from the cities. We have many studies that shows really that the reduction of, let's say, greenery, a reduction of ozone because of the greenery in different parts of the world can be of the order of magnitude of 2 or 3%. But at the same time, we know, for example, that the increase of the, of the structure, when it really is not irrigated and when it really is not taken into account the emission of the BVOCs, may, let's say, raise the temperature and also raise the heat-related hospital admissions and so on. So we may have some adverse effects of the greenery, especially really during heat waves, if trees are not really treated the best way. And of course, there is a scientific background around it. We know how this happened. We know how BVOCs are, let's say, emitted. And we know really the chemical nature of BVOCs. These are isopropanoids, which really interact with nitrogen oxides and create ozone. And in many parks during the very last years, especially in Europe, that we have data, shows that inside, and around the parks, non-irrigated parks, the concentration of ozone is maybe increasing up to 30 or 40% during heat waves. So, and this is a very serious problem that really has to be taken into account when really greenery is, let's say, increasing in the city. And we have to protect the population, because if we don't do that, we may have adverse results. I'd like to show you some results, for example, from, let's say, Berlin, where they measure the concentration of, let's say, ozone and BVOCs during, let's say, periods of high temperature. You see that the concentration, the BVOCs and the concentration of ozone during normal days was at this level here. During, let's say, a hot day, during heat waves, it increased by a factor of 3. So this is a major problem, because the increase of the concentration, of BVOCs, which results in a concentration of ozone, is a killer, is killing people. So this is something that we cannot really forget. Given the expected overheating, different, let's say, forecasts future shows that the emission of the BVOCs around the world may increase up to 10%. So this is really something very important. And I'd like to show you another study, very serious study, which shows the increase of isoprene. Isoprene is a BVOC, which is caused by urban greenery. And you see, for example, inside the urban forest, that there was a tremendous really increase compared to the urban background. Inside the park, the, let's say, concentration of BVOCs was really 3 to 4 times higher. And it was really 5 times higher than in a highway, where we expected to have much higher concentration. So while greenery helps to decrease really the concentration of different pollutants through different mechanisms that I don't have the time to go through, but mainly through deposition, you know, we have at the same time understand the whole, let's say, physiological life and interaction between vegetation and, let's say, greenery. There are different processes which take into account, have to be taken into account, these biogeochemical, let's say, processes, which really increase or decrease the level of the pollutants. And actual, let's say, simulations and measurements show, for example, that when trees are under stress and their surface temperature is much higher, the leaf temperature is much higher, you see, for example, that when the leaf temperature is increasing, there's a tremendous increase of the BVO system. The other issue that I like really to mention and discuss a little bit with you is the social impact of greenery. All around the world, there is a very, let's say, direct association between income and greenery in specific neighborhoods in the city. And I show you, for example, the results from Athens. Rich people is living in areas of, let's say, high greenery. This is what I told you before. And this is very clear from studies, for example, in Los Angeles, that shows, for example, that when, let's say, the income is high, the evapotranspiration is really very, very high. It's tremendous. While when you're living in an area of low income, you don't have greenery. This is important because it defines also the social impact and the results that we've seen before. I like to stop about urban greenery and present you some, I have 5-10 minutes, present you some estimates about the future of green spaces in the world. We know that the critical temperature beyond which photosynthetic machinery in tropical trees begin to fail is 46.7 degrees. What does it mean that? When really temperature is above 46.7 degrees, trees, they stop photosynthesis. They don't really increase the temperature. They don't really just increase the temperature. They stop photosynthesis. They don't produce any oxygen. Do we have such a problem? There are studies actually performed, especially in tropical climates, but it is quite unclear if leaf temperatures experienced by tropical vegetation approach, and they have really such a threshold. We found through measurements that the temperature inside the canopies, let's say, may present a temperature close to 34 degrees, sometimes approaching really 40 degrees. For the time being, only 1% of the time temperature exceeded 46.7. But it is very important really to show from the tropical climates what really happens during the period of very high temperatures. During the period of very high temperatures, you see here, transpiration becomes negative. You don't have any thermal effect, but you don't have also any oxygen produced really by the trees. And unfortunately, because really the forests we have, they have a high age, are quite old, for example, they don't contribute the same way. Forests in US or in Europe will no longer absorb, let's say, carbon dioxide after, let's say, 50 years, because really they stop having this potential. So in order really to increase and enhance the sink potential, the cooling potential of trees, we need really to replant. We need younger trees. If we don't do that, unfortunately, in the future, the contribution, not only the, let's say, cooling contribution of trees, but at the same time, the overall ecological contribution, photosynthetic contribution of trees will decrease tremendously. And the mitigation potential of vegetation, their physical effects, will be very much influenced by the background climate and by the global warming. From the data we have, it shows that really, because of the increase of the temperature, trees will lose a very high potential of their cooling effect. Why? While, increase of the CO2 in the atmosphere, it acts really a lot and helps a lot trees to, let's say, it works like a fertilizer and increase the, let's say, the green surface. But the increase of the CO2 in the atmosphere has, another negative effect. And this negative effect is that because of the higher concentration of CO2, the stomata of the trees closes to be protected. So although you may have, let's say, higher percentage or higher fraction of trees in cities or in tropical forests, these trees will not evapotranspirate. So this is a major problem and shows, for example, different scenarios which are published in Nature, very serious, let's say, journals. So that in case that we may have an increase of CO2 up to 1,000 ppm, a huge increase, now we are close to 450, trees may contribute to heating and may contribute really to very important, let's say, heating. So we have to be very careful in this planet about, let's say, our, let's say, forest and the way really that we have to take into account. If we don't really stop the increase of the CO2, trees will not really help anymore the ecological, let's say, performance of the planet. And those stupid guys that they have, let's say, proposed, let's plant 5 billion trees, etc., and save the planet, they just say silly things. Because once, the concentration of CO2 is increasing, trees will stop to evapotranspirate. So trees are not robots that produce, let's say, coolness and help to decrease the temperature under any conditions. No, we have to respect their physiological life. And if we don't understand it, and if we are using and promote simplistic solutions, we may have tremendous, let's say, surprises. So several studies, very simple, very, let's say, complicated and very, let's say, sophisticated studies showed, for example, that if we don't really decrease the CO2 at the atmosphere, we may have a major problem, regarding the evaporative cooling from not only the urban trees, not only from the urban forest, but also from, let's say, the tropical forest. As it is mentioned, by an excellent contribution published quite recently, the contribution of plants to changes in future extremes will depend on the responses of vegetation growth and physiology to the direct and indirect effect of elevated CO2. The conclusion is that vegetation responses to a 4-time increase of CO2 increase summer heat wave occurrence by 20 days or more, 30 to 50% more of the radiative response alone. So trees, if CO2 is increasing, will contribute to increase the heat, really, the hot spells and the heat, the extreme heat and the heat waves. It's not so simple. It's not only that we need water. We need really to decrease CO2. So it is really complicated, and the message is very clear. Trees contribute a lot to cooling, shading, evapotranspiration. But there are rules, there is science, trees, they have their own, let's say, science. And trees really, sorry. Needs really to be protected, maintained, and respected. It is a wonderful mitigation solution, but needs really a scientific approach, not only at the urban level, but also at the planetary level. And the conditions are not really the best possible because CO2 is increasing very rapidly. And trees under very high CO2 concentration would not contribute anymore to cooling, will not contribute anymore to produce oxygen. I will be happy to reply to your questions.
Anybody has questions? What are some of the common challenges associated with implementing large-scale green and blue infrastructure projects? How can these challenges be addressed?
The challenges by implementing large green and water, Can you repeat the question, please?
What are some of the common challenges associated with implementing large-scale green and blue infrastructure projects? And how can we address these challenges?
I think that this is what I have really elaborated during these 2 hours. The challenges, are really a lot. We are positive and we have negative effects. You may, let's say, by having some, let's say, natural-based solutions, you may have some good results. You have to understand which is the magnitude of the results, which is the real impact. Don't expect 10 degrees and things like that, stupidities. On the other hand, a real contribution. The contribution is not only, climatic, it's ecological, it's psychological, it's on health. Important things, very important things. But there are limits. And there are conditions. If you don't respect the conditions, don't expect really to have benefits. If you don't feed trees the proper way, you will not really have the potential you wish. So the, let's say, silly ideas, let's plant trees and we solve the problem, it doesn't help at all. You need really to support trees the proper way. I repeat it many times. You have to respect trees. Don't plant it and leave it there. Don't contribute at all. It's like you take, some, let's say, workers, put them on a field to work, and don't feed it. They will stop contributing. They will stop working, So the message is clear. I will not stop really mentioning it. Urban greenery, say science, is something really that is very complicated and is a scientific, let's say, thing. It's a science. Don't consider that it's very simple. It's not something simplistic. Don't follow all those, let's say, silly guys that they say that put trees and we solve the problem. It is very important to put trees, but you have to know how to do it. You have to do it in a scientific way. How to tell this to policymakers? They push things. I'll tell you my personal, let's say, my personal experience. In Australia, they like very much greenery, and of course, it's very good. And there was a plan, especially for Sydney, to plant 5 million trees. And the government really asked our university, our laboratory, to perform the study. We performed the study. I showed you some of the results. And we explained to the politicians, that they can plant, some trees, 2 million trees, 5 million trees, exactly the same thing. and the corresponding, results, what they expect, 1 degree, or, 40% increase of the water content, etc., etc. We done it in a very scientific way, in a very, let's say, fair way. And I presented this, to the local government and to the Prime Minister. The plan has changed. The plan has changed because once they got, the knowledge, and they see that they will spend tremendous amount of money to do something that perhaps will not help so much, they reduce the program, they size the program the proper way, and really they optimize the program. So we need really to communicate all, the, let's say, impacts, the benefits, the drawbacks to the politicians in really proper scientific way. Once they, let's say, give them the proper values, the proper figures, they will understand.
It just looks like we are back to ground zero. Like I feel I don't know anything. And I wonder what I'm going to teach the students after this lecture. So that's what I feel. I mean, because this is also contextual. You are telling to the geography that you have done work on. I'm not sure whether for this geography of India, this work is done. And India is also very vast. So whether I don't know. This class has really got me into an existential crisis, really.
Professor, what you have to, in my opinion, of course, who am I really to tell you what to do, but what really is important is really to give them the scientific knowledge. And then if they like really to become experts, they can really go deeply and understand what is happening. Without the proper scientific knowledge, they will not really act the proper way. There is no any other way to do it. They have to understand what really happens. If they don't know what really happens, they will make little stupid things. And they have when we have illusions, especially in science, we make big mistakes. The scientists should stop having illusions. Should really based on scientific knowledge and practice.
And I also feel, I also have realized the importance of basics.
Yeah, you're right.
And how architecture or urban planning is such a multidisciplinary subject where we need botanists, we need building physicists, everyone to come together.
Issue, and I see the problem, almost every day because I'm in a school, for built environment, and we have planners, we have architects, etc. They have their own way. They have, their own rules, and they have their own beliefs. Climatic change has changed completely everything, the climate of cities, and so new data are coming here, new conditions. So all these new conditions and all this new knowledge have to be integrated into landscape, and urban planning and things like that. This is not done for the time being. But the best way to work on it, because working with, let's say, in large projects around the world, is to have the interaction, to work together. So now, the design, in a city is not just the privilege of city planners. It's not just the privilege of landscape architects and landscape engineers. It's not the privilege of climatologists or whatever. We need to work in an integrated way, in an holistic way, all together. So we transfer the knowledge from one to the other. If you just leave, one discipline to do something, they will make mistakes. If you leave, for example, the epidemiologists to do something, they will make mistakes. If you leave, just the climatologists on the engineers, they will put everywhere, machines. So we need really to work together because now the problems are multidisciplinary and interdisciplinary. And there is no discipline that knows everything. We know something, but we can exchange knowledge between us. And at the end, the group may have a very good understanding.
Right, Professor. So you have left us extremely humbled, and you have left me very ashamed of how ignorant I am and how I have to start learning again. Thank you so much. And I'll wait for another ego bashing tomorrow from you. And thank you so much. It was wonderful. And I'm getting lots of WhatsApp text messages saying what a fantastic session and eye opener this session has been.
Thank you so much. Yesterday, I sent you the book about, the materials. You can distribute it for free to the others.
Yes,
Okay?
yes. So we will make a small compilation of everything, and in the end, we will send it to everybody.
Good. Thank you.
Okay. Thanks.
See you tomorrow.
Yes, yes.
Thank you, sir.
Thank you so much.
Ma'am, can we go for the next?
Yes, yes, yes. Please, Claire.
Dr. Faiz, are you ready?
Satvik, please text. Mr. Satvik, please text because the next session is going to start. Revati madam, please text in the chat box because the next session will start.
Okay, I will request all the participants to mute themselves. Satvik, sir, kindly mute yourself. Can anyone? Yeah. Thank you. Thank you, participants, for joining us. Now we are moving ahead for our next session, and the next session is about energy efficient cooling strategies in the canopy layer, a case study approach for UHI mitigation. So our next speaker is Dr. Faiz Ahmed, sir. I would like to introduce him. So Dr. Faiz Ahmed sir is in faculty in Department of Architecture at the School of Planning and Architecture, Vijayawada, an institute of national importance under the Ministry of Education, Government of India. He holds a PhD in Architecture and Planning from Anna University, Chennai, along with an M.Plan, MS France, and BArch from reputed institution. His areas of expertise include urban microclimate, 3D city modeling and simulation, building and urban physics, geospatial analysis, thermal comfort, and energy efficiency. He has over a decade of teaching, research, and consultancy experience and has co-funded Formation Studio for Architectural Practice. Dr. Faiz is the project director of ICSSR funded project on post-tsunami housing reconstruction and livelihood revitalization in vulnerable Indian coast. He is also a principal investigator for Government of India project on cooling strategies for Hyderabad to mitigate urban heat island effects under the Amrit scheme. Internationally, he has contributed as co-investigator in the CREST project funded by the British Council and as member in EU-funded REUCOM project on resilient urban communities. His publications record is extensive with contribution to reputed journals like Nature, Communication, Earth and Environment, Urban Climate, Land Use Policy, and international conferences including ICUC and IDRIM. He has supervised doctoral research in areas such as outdoor learning environments, flood-sensitive planning, and urban soundscape, and has organized national and international conferences at SPA Vijayawada. He is recognized with several awards and fellowship also. Well, I would like to welcome Dr. Faiz for the next session. Welcome, sir.
Thank you, Dr. Prashanti. Am I audible and clear?
Yeah, you are audible.
Thank you. Let me share the screen. Please give me a confirmation. You can see my screen.
Yeah.
Yeah. Okay. Yeah. First of all, I would like to thank Vijay Lakshmi ma'am for the opportunity, and it is indeed an eye opener for me as well. And there are a lot of things that I've also understood in these sessions from Professor Matt. And what I'm going to present today is one of the projects that we are working on. It's called, uh, just a second, yeah. We are calling it as Cooling Strategies for Hyderabad. And this is one of the projects funded under Atal Mission for Regeneration under Center for Excellence here in SK Vijayawada. And I'm leading the team, and we have other members as well who have contributed significantly to put up all this that we have understood, but that we are presenting it to the Hyderabad city. Okay, the structure of the presentation, I'm to keep it in brief. We'll just very briefly discuss what is the context in which we are trying to address this issue, and what is the key objective of this project, and how we have approached this project, and how we approach this in Indian context, and what city planners do, and how this is slightly different from the approach that we conventionally do in Indian case. I'll be highlighting that, and we try to integrate both surface temperature and air temperature. And I think in the last lectures as well, in the first lecture, there was a lot of discussion about how we can how we have to look at both things together. And we have developed we have tested several strategies that is available in this context, and we came out with some solution metrics that can be implemented. There are strategies that did not work, and there are strategies which worked, and there are strategies which worked but very minimal impact. And the last lecture has given me some more confidence to present the outputs in a way, because some of the strategies which we did not give any result. So when we presented that in a bigger forum, we had some critical issues on that. Anyway, so what is the background? The case is Hyderabad, and we have experienced the temperature raising more than 40 degrees Celsius on several days and so on. And also the build-up has increased significantly over a period of time. So, and persistent night heating and UHI has been well documented, and is one of the problems that has been there for quite a long time. And this has been a case in other cities as well, in other Indian cities as well. And we are quite familiar with this kind of issue. Okay, first thing is we are trying to discuss this under a broader aspect, what has happened over a period of time. But if you take out the data from 1970s to till 2024, we're just trying to plot. If you take the anomalies, there has been only a slight increase in the overall temperature, an average, if you see. But if you see the data closely, the summers have been much severe in the recent past, and this was also pointed out in the first lecture by Professor Matt on how this has been recorded in other cities as well. So if you look at the broad spectrum, this is for Hyderabad case only. The net increase is not so significant, but if you look at the summer, the intensity of summer, or the frequency of heat waves that has occurred, that is quite severe. This is first point that I would like to place here. The second thing is, if you put the temperature and the humidity data together, and of course we have severe summers. Okay, that's known fact. And what we also observe is, in addition to the higher temperature, we also have a low humidity that is happening that is observed in Hyderabad case. And in the morning session also, and this was referenced, how low humidity can have a more impact other than just drier air or other than just drier temperature, it will have an impact on how vegetation also works. So this is something which is also something that we have to look in. It's not only about the temperature, and we should also look at how the humidity plays around. And this is only with respect to the summer time. But if you look at the other time, there are cases where the humidity raises to 80, 85, 90 in touches and all. So we are trying to discuss more on how do we address the issue of heat during the summer months. So this is second thing. The third thing is what is the objective of this project that we are trying to do is to develop an evidence-based strategies that can be implemented in Hyderabad. So with which we went around to identify some of the hotspots of the city. I'll present to you how those hotspots have been identified, and we approached after identifying hotspot. We wanted to understand how the heterogeneity in the city works, and like Professor pointed out, within the city we will have different urban settings, different greeneries, different water body combinations, and so on. So how do we identify that different characteristics within the city, and how do we arrive at how do we arrive at strategies that may work for those heterogeneous urban environment? This is the overall methodology that we have tested, and once we have these strategies in place, and we have developed some metrics that the Hyderabad city can implement in coming years. Okay, what is the conventional way of approaching this subject is to identify hotspots and identify the UHA intensities. And most of the time, we have seen that the city planners use Landsat data, Moody's data to understand how these UHA intensities can be measured. And most of the time, it is the surface temperature that we record and compare. And one of the common things that we try to do is to map how the building density has changed over a period of time, how the vegetation index in terms of NDVI, how it has changed over a period of time. So this was also pointed out in the morning, how the NDVI index can be used as one of the measurables to check where are greens and what are the cooling potentials of these NDVI. Similarly, what we also do is to understand the land surface temperature. This was also pointed out in the second day or so, where how these surface temperature can give a lot of insight on what's happening in different parts of the city. And most of the time, what we do is we use this and then arrive at the hotspots and the UHA intensities across the city. So this is one of the steps that we also tried to do in case of Hyderabad, and we came out with what are the hotspots and what is the UHA intensity for last 2-3 decades. In addition to that, if you see, this is daytime temperature. Okay, let's be clear. The surface temperature that we are trying to that I'm trying to put up here is the daytime temperature. But what happens to the temperature during the night time? That's also something that we have to understand, right? So we use Moody's data to understand how these temperature what is the thermal environment during the night time. So if you look at these slides for 2004, 2014, and 2024 during the daytime, during the afternoon hours, and also during the night time, we mapped the changes in the temperature profile across the city. And you can also see the difference in terms of year. For example, in 10 years, you can see how the change has occurred in terms of the temperature across the city, and what is the intensity of these temperature during the city during this period. And same happens during the night time as well. You can see the concentration of heat at 10 p.m. Concentration of heat in the later night as well. This is one thing. Second thing, if you see on the right hand side, I have put up the sections through the city, just to understand what happens. It's not uniform throughout the city. Right? There is variations in the surface temperature also across the city, depending on the build form that we have, depending on the vegetation cover that we have, depending on the water bodies that we have. So the urban heterogeneity also plays a big role in how we understand the heat that is there in the city. So this is second one. So in the first thing we use Landsat, and in the second layer we try to document these thermal variations during nighttime using MODIS data. And in addition to that, we also took the live data, meaning the automatic weather station data from Hyderabad city. Fortunately, there were about 150 weather stations in the city of Hyderabad. So we could purchase these data to from different. These are the different weather stations from which we have taken the data, live data, and then we used it for validation of our work. And this was also again pointed out by Professor in the lecture that the reliability of ground level data becomes very essential to say something which can be as realistic as possible. So we have taken some data about 17 weather stations within the city of Hyderabad and on various variables to document it. So some data that I have just plotted here, 2014-24. What is the variation in the temperature for the same day in 2014 and for the same day in 2024? Okay, so how the concentration of these islands are changing, especially in a decadal time. So we have three results now. One using the air temperature, the automatic weather station data, AWS data, and then the MODIS data and the Landsat data. And if you look at the result, we could find a variation in the air temperature by about 2.7 degrees Celsius. But if you look at the MODIS data, we could find the UHN intensity of about 6 degrees Celsius. And if you look at the Landsat data, we were able to compute the UHN intensity of about 9 degrees Celsius. So on an average, there is an UHN intensity of 3 to 8 degree difference across the city. Now, how do we capture these variations across the city? For example, like I have been saying that if you take out a section across the city, because of the different urban heterogeneity or urban density, green cover and blue cover, the surface temperature varies. This is Hussain Sagar Lake. For the ones who are not aware of the geography of Hyderabad, this is one of the lakes, famous lake. You can see how water body can bring in the surface temperature down by significantly. This can you can see there is a difference. There's a dip in surface temperature. Also, you can see because of the green cover how the variations can also be brought. This is understandable, green and blue. But if you look at the urban fabric, also there is a variations within the city. So how do we capture these variations and how do we map this urban microclimate conditions within the city is something that we wanted to try. So in the second objective or in the second layer, we wanted to capture how these variations occurs in a canopy layer and how local climate zones can be identified within the city so that we can develop some strategies that are very, very specific to those neighborhoods, not the generalized strategy for the entire city. So if you look at the theory also, if you imagine if this is the entire city, and if you zoom to one of the urban areas, you can find that we have buildings, we have vegetation, we have narrow streets, wider streets, and so on and so forth. Okay, so this is in a technical way, these are called local climate zones, right? Local scales. And as architects, what we are interested in buildings and the immediate context of the building. But all these fits in the entire city fabric. So from the theory, from theories and from other studies as well, the urban morphology plays a vital role, or it has a significant impact on how these strategies going to work. And also, not all, there's no one solution to all. This has been repeatedly been mentioned and presented in the last 4 days as well. The solution has to be tailor made. It has to be specific to the urban areas that we have. So we also wanted to adapt a similar strategy in our project to arrive at more context-specific solutions. And why do we do that? And do we have supporting arguments for this? This has been again well documented in other literatures as well. A lot of studies have shown that UHI intensities are found much severe. UHI intensities are found in LCZ 2 and 3 categories, which are compact mid-rise and compact low-rise categories. And at the same time, a lot of solutions have also been worked out for these specific LCZs. So in addition to that, we can, once we are able to identify what are the different the climate zones that we have within the city, we can also map what kind of strategies may best suit for those climate zones within the city. We are not talking about the bigger area in general, but within city, if we are able to identify what are these, how these local climate zones are formed, and how once we are able to identify such local climate zones, we will be able to suggest an appropriate strategy that may work in those local climate zones. So we adapted, again, this is a well-established process in the literature. We can divide the city into 10 urban fabrics and 4 vegetation fabrics and 2 lands and water body. So like we do land use classification, we have to do this kind of classification for the city fabric. What are the properties that is used for classifying? It takes into account your sky view factor, canyon street aspect ratio, mean building height, your terrain roughness, building surface fraction, impervious area, pervious area, and surface albedo, and also anthropogenic heat into the context. So when we divide these the city into the local climate zone using these variable, we'll be able to understand the city in terms of the microclimate formation, and probably come out with strategies that may work appropriately for that. So what is the result that we got in classification? You can see this is for the entire city of Hyderabad. We found LCZ2 about 76 square kilometers of built area falls under LCZ2 category. LCZ2 is compact mid-rise, and LCZ3 is more than 100 square kilometers of built up area falls under compact low-rise category. So if you are able to come out with some strategies that contributes, that forms major portion of the city, probably we'll be able to. We are trying to address a major part of the city fabric. What we did is we did not give solutions to the entire city. We wanted to identify a hotspot within the entire city, and wanted to demonstrate in one of the wards one of the area of interest, which included 3 wards, to come out with strategies that can work in this particular area. So if you this is one of this is the area of study. This is the area of focus where we have tested all the strategies that we wanted to apply for the entire city of Hyderabad. So we have the LCZ classification for our area of interest, and we have documented all the building fabric of different land uses that you can see here. If you look at this here, in terms of local climate zone classification, these are the different types of local climate zones that we can observe in our area of interest. And these are different neighborhoods that we have identified, where we have went into details and documented those neighborhoods, and then tested our strategies. And what are the strategies that we have tested? This is another thing that requires discussion. Based on the case studies and based on the several case studies that has been tested on this line, we wanted to test how green roof works, how green wall works, how what is the street tree combinations that we should have, roadside vegetation, pocket green, all of it what was discussed in the morning. A lot of things have been said in the morning as well. We wanted to check how this can be integrated in a more meaningful way, and it's not something new that we are trying. This has been tested in other cities like Mumbai, Chennai also. What results that they have got, and can we come out with some? Can these strategies again work? So when we say vegetation, we wanted to try several ways in which vegetations can be integrated into the city fabric. One. The second one is the blue infrastructure. Like I said, although this is a composite climate, the climate of Hyderabad, but during the summer it becomes very, very dry. And I also showed in the beginning that the humidity level goes down below 20, and the air becomes very, very dry. So we need some humidity, and again, this is something that adds value to what I've been saying. That vegetation also requires water, like Professor said in the morning. Though we may have a good vegetation, maybe if we have a low humidity and if the air is dry, and these vegetation may not work. So particularly in case of Hyderabad, when we did an assessment, and we found that this issue also has to be addressed. It's like a desert climate during summer months. Okay, at least for 1 month we have such a situation. That also has to be understood, and we need some strategy that can work for that particular. Of course, it is a seasonal intervention, but we think that that needs to be addressed as well. So we tried fountains and misting systems in the model to check whether we can get some benefit out of this. And the third strategy that we tried is, of course, cool roof, cool paints, and cool pavements of different varieties on the roof, on the pavements, on the walls, and the facades that we have tested these combinations. And these are applicable in existing case as well. All these three strategies can be tested in existing case. And we also came out with some strategy that can be applied in a new case. For example, let's say what should be the aspect ratio, sky view factor, building height, and what could be an ideal orientation if a new city is being developed. Actually, in Hyderabad, there is a commissioner, or there is a commissioner set up for future cities. They are coming out with a new layout, new city formation, where they are trying to push create a new city formation in some parts of the city. So these ideas can also be taken into implementation in new development or greenfield development. In addition to that, several studies in India have shown how shading can help in a large way. Okay, these are uh, uh, very simple strategies that can be tested, and it has been tested in several cities as well. Shading can help in a long way, at least during these summer months. Okay, so what we did, we used environment simulation for all this modeling, and we also had taken our mobile weather stations to collect primary data, and of course we have used extensive data from the local automatic weather stations across 155 weather stations the Hyderabad city has. Okay, so what are our samples? For example, let's say if you take out one urban area of about 40,000 square meters, it's about 200 meters by 200 meters we have taken for modeling. And you can look at the variations in the urban areas, the characteristics of urban form. One urban form is not same as the other. Okay, all these six images that you see is of same area within the city of Hyderabad. So we can't have the same strategy here, same strategy here, same strategy here. So that's the idea that we wanted to bring in, and we wanted to check what are the combinations of strategies that can be suggested if you have high heterogeneous urban environments like you see here. So we went down to map the areas and developed models, and then these are some of the settings that under which all the simulations have been read. And we have used NVMet where we can simulate about 52 variables of different characteristics, including air temperature, mean radiant temperature, surface temperature, relative humidity, and PET, SET. So a lot of variables can be taken up, and a lot of things can be simulated using this. And one of the index that we have used to compare all our results is PET. Although we can use other parameters, PET is one of the parameters that has been tested, and in several literatures we found that the reduction in terms of PET, because we are trying to measure at 1.2 meters level. So we wanted to make sure that this is perception of heat at 1.2 meter is checked. We could have done this at air temperature or surface temperature as well, but we restricted to the PET, SET, UTCI values as well. We do have comparison with air temperature, but the result that I'll be presenting will be by keeping PET as the common denominator for a comparison. So some initial result, I think you guys must be aware how the NVMet results are generated. Before we actually go into the strategies result, one of the thing that we should also get an understanding is how these strategies will have an impact on indoor conditions also. Okay, this has been pointed out in the presentations as well. Whatever we do in the outdoor environment have great implications on how the indoor conditions are framed, how the energy consumptions are being made in indoor conditions as well. So to do the concretization of that statement, we have two graphs that you can see. Both are taken from the same study area, just to demonstrate why the strategies in outdoor environment have a profound impact on what happens inside. So on the left hand side we have a residential building, okay, and the right hand side we have commercial building. You can see here. So these are surface temperature. This is air temperature, surface temperature, air temperature, and this is indoor air temperature. The bottommost third line that you see is indoor air temperature. What happens? This is a glass building. You can see this is building B. This is a glass building. This is a typical apartment building with conventional windows that we have. What is the difference here? You can see that the in case of the apartment building with a typical window size and that we have it like in most of our Indian cities, what happens to the indoor temperature? You can see the peak indoor temperature reaches during the evenings, about 6 or 7 in the evening. You can see that the temperature reaches to about 36 degree or so. Okay, whereas your glass building, what you see here, your 36 degree or the indoor temperature that we see here that happens in the evening comes or reaches the building, the indoor temperature, ambient temperature reaches to about 36 degree even in the morning itself. Why? Because of the poor choice of material that we have that we have in our building. Okay, it's not only about how we do, what kind of strategies that we work in the outdoor condition. It also matters how we use these materials, how we select the building materials, how we select the building materials for the glass, roof, and windows as well. A lot of it has been discussed in a very detailed manner in last several sessions. Okay. Another thing that we have to understand is when we apply strategy, some strategy may give result, some strategy may create problems. And I'm happy to be confidently presenting this now because I can see that this is not something new that we got. Some strategies are giving negative results, although this has been promoted as the best results possible. So, for example, let's see here. We have three things plotted. This is one is existing case, the other one with a cool roof, and the other one is with a cool pavement. So what happens? We have potential air temperature and potential air temperature for the base case, potential air temperature for the cool roof case, potential air temperature for combination of cool roof and cool pavement. So which is the orange line that you see here. I think that's not much of a variations that you can see in terms of air temperature in all three cases. But there is a difference, 1 degree difference that has been that itself is a significant contribution. But we will come to this later. But if you see, if you go only by this parameter, we may be trapped. We may have a negative, or we may have wrong conclusions by looking at only this parameter. However, if you see the other parameters, for example, let's say mean radiant temperature. You can see this is the mean radiant temperature, and you can see if you use this is base case and the cool roof case. This is base case and base case plus cool roof plus cool pavement. So there is an increase in mean radiant temperature. Okay, so maybe it is helping in one way, but it is creating a problem in another way. So this has to be we have to see the impact in a clean manner, and then we can say whether the strategy may work or may not work. If you go only by temperature, or if you go only by MRT, or if you go only by other parameters, we may end up suggesting something which is good for in one aspect, it may not be good in other aspect. This again, for example, let's say I've been saying humidity is a cause of concern for Hyderabad case, particularly in summers. But if you, for example, let's say this is humidity level in an existing case, which is about 25%, which itself is low. But if you use the combination of cool roof and cool pavement, the humidity level goes further down. So here it is a problem. Even if you use this it may have a beneficial impact, but we are also creating some kind of other problem that also should be kept in mind when we suggest something in specific. Okay. So like this, we did an assessment for 13 different neighborhoods within the area of interest that we have identified. 13 neighborhoods have been modeled like this, and all the simulations have been done for these 13 neighborhoods. And we did a comparative assessment of all the parameters starting from impervious surface area, pervious surface area, and what is the building density, in all that. Most of our comparison will be on PET and surface PET only, to check what is the variations that we are getting in implementing some or several of these strategies. Okay, and that is with respect to the entire neighborhood. We also did. We also took a street as an element, and then we wanted to do interventions on certain streets which are commercial, which are frequented by pedestrians. And how do we bring comfort at pedestrian level by having some intervention that is very specific to the street combination. So we identified a street, and we did, of course, we did a simulation, and we also took several measurements during the summer months to check what is the validation of the simulation and also the measurements that we have taken on ground. What are the strategies that we tested for street? This is the base case, and in addition to the base case, we wanted to add trees. For example, let's say 50% of the trees, meaning trees at 7 meters distance without touching the canopy layer. Trees which are just touching the canopy layer, it's not overlapping canopy layer. And ground cover, if we there's a lot of fascination for suggesting ground covers for doing the beautification of the city. You must have seen in several cities, especially the roads which is leading to airport. This kind of interventions has been pushed from the government, and we try to implement it. So what is the impact it is going to create? And if we go only by shrubs, not by mature trees, what is the impact it is going to create? And we have seen from the other studies also that shading can give a lot of relief, particularly in junctions. So how do we bring in shading in the street so that we can extract some benefit out of it? And of course, all different materials, pervious materials, reflective coatings have been tested. Okay, so in summary, what are the strategies that we wanted to test? What we have tested is cool roof as one of the strategy, cool pavement as one of the strategy, cool roof and cool pavement together as a strategy. Why this combination? Sir pointed out in one of the discussions that if you have high-rise building, maybe this combination is not okay. The effectiveness of a cool roof is limited to a certain level. But whereas if you see the case of Hyderabad, it is mostly compact low-rise or compact mid-rise. So where we can have a combination of both your cool roof and also cool pavement in low-rise areas. So we made a combination of strategy to check whether this can work, and we also tested pervious pavements. And we also applied, in addition to cool roof plus cool pavement, we also added cool wall in southern wall, in only on southern wall, based on the solar radiation studies that was done, to whether this can also help in certain way. And of course, we tried with water body, and in the new layout, what is the impact of orientation that's going to create. And also in the morning also it was pointed out, having green pockets can be an effective strategy. So introducing a green pockets, not like a large one city level parks, rather than having a micro green urban pockets can be beneficial. So we check that as well to see what is the output that we are trying to what is the output that we may expect if we implement this. In addition to this, we also tried green roof. There was some discussion about green roof as well in the morning, and it is, of course, a very cost intense strategy, not cost effective strategy. Similarly with green walls as well, these are maybe for like affluents. So and sunshade as a shading strategy, and lot of combinations of trees and vegetations to check which combinations may work in these neighborhoods. So these strategies were applied to the building model that we have taken for all the 13 neighborhoods. This has been all these strategies have been applied. So we'll quickly see some of the results for each of the strategy. I'll not go into details of each of the results, but I'll just highlight some strategy in each of the neighborhood, and I'll just very quickly go through which worked, which did not work. For example, let's say this is one of the neighborhoods in the Hyderabad. You can see this is the base case. How do we read this graph? You have a base case here. This is existing case. The first assessment was done to analyze what is the existing case. So keeping that as a zero as a reference, these strategies are added. If we add cool roof, we got a PET reduction of about 0.16 degree difference. So if we added cool roof plus cool payment, the PET decreased by, see here, when I say decrease and increase, I think we should understand this is from the positive aspect. Okay, so there's an improvement in the cooling by about 0.35 degree difference. But if you see, if you apply only cool payment, the PET value decreased. It added to discomfort. Similarly, if we see here, the trees, when we added trees and also all your cool roof and cool pavement and greenery, it actually added to the discomfort. So what was the most effective strategy that worked in this case was cool roof plus cool pavement and green roof, with which we were able to bring the PET value by another 0.5 degree difference. And if we apply only green roof and cool roof plus cool pavement, we were getting an PET reduction of about 0.3 to 0.35 reference. Similarly, if you see in other neighborhoods, the only strategy that worked was cool roof and green roof and green floor. Here means the ground cover that we had applied. So whereas if you apply other strategies, we found that the PET values it did not improve. It actually caused more discomfort when we apply these strategies. So these strategies were not effective in this area. Similarly, if you in one of the neighborhoods when we tested, none of the strategy gave any. None of the strategy were effective. In fact, it increased it increased the PET value by 2 to 3 degree Celsius. Okay, so in these neighborhood, we're trying to find out what could be the reason and what has gone wrong in this case. Similarly, in other case also, when we applied all the strategies, none of the strategies gave an improvement from the existing case. Okay, so maybe from what was Sir said in the morning, even I'm now thinking whether it is because of too much of dryness in the air or the other things. We need more. We need more data to explain why this is happening. This second thing. In other strategies, we can see similarly we were able to get some benefit by appropriate placement of trees and vegetation, and some impact on greenery. Similarly, like this, we did for all the 13 neighborhoods that we have identified. In some neighborhoods, we were getting results, improved results in PET for all strategies. Although this may be very fractional, there is slight improvement in PET values by adapting all these strategies. Well, for example, in other neighborhoods as well, you can see a lot of strategies, a lot of combination of strategies or individual strategies seems to work in this particular case, especially in this case where you have LCZ4. A lot of strategies, in fact, all strategies gave a positive output from 0.8 to about 2.5 degree reduction in PET values. Like this, we did for all the 13 neighborhoods that we have studied. What is the overall observation from, these are from the neighborhood study, and some observations, overall observations from the street level interventions. I've put up a matrix here. How do we read this matrix? We have, this is for vegetation, and we have parameters for comparison here: air temperature, relative humidity, MRT, UTCA, and PET values. On this side, we have the strategies, which was by having only trees, what is the impact it is going to create? By having trees plus ground cover, what is the impact it is going to create? By having 50% trees and ground cover and shrub, what is the impact it is going to create? Here, 100% trees means trees at a 7-meter distance. Okay, and this is much further than that. And we have only ground cover, and this is the base case for comparison. So if you see here, if you go by only trees, we can improve. We were able to find from the simulation results that there's an improvement in PET value by about 2.5 degrees Celsius, and also you can see there's an increase in RH value, which is also required in case of Hyderabad, particularly during the summer months. Okay, and also if you see in other strategies, we can see some improvement in PET value, but whereas in other only for ground cover and shrubs, the results were not that significant anything. Other thing that we should also we found is the MRT value also should be low. We were trying to be sure it's not only about PET, the MRT value, the reflected value, the reflected heat also should be low. So vegetation had that impact that you can see from here. And when it comes to the temperature, we could find about 2.5 degree reduction in air temperature, and when we use trees, and you can see the other results here. This is for the vegetation, and this is for the surface. Although these are the combinations of strategies that you can see here, and you can see there's an improvement in PET by about 1.5 degree Celsius. But although there's an increase in benefit in terms of PET value, but there is a significant increase in RH value, and also you can see there's an increase in MRT value. Okay, so these strategies are making the environment more drier, and which is also not good, as we have been pointed out. Okay, other strategy that could work in the street was the shading. Shading gave a significant improvement in the PET values, where about 4 degree difference, or 4 degree improvement in PET values we were able to observe. And when I compare with other index, UTCI gave a significantly higher numbers. Since we are using PET value, we are trying to discuss only the PET values here. And also the other impact, other thing that should be kept in mind is it also brought down your MRT value by significant number. Okay, it's not only improved your PET value, it also brought down your MRT value. So when we this is for the strategy, shading strategy. And when it comes to water body also brought in a significant impact in PET values. It improved the PET value by a big number, and of course it has increased the RH value. And we wanted it also, and this is what we wanted when we at least during the summer months, seasonal months, we wanted to improve slightly the humidity levels there. We don't want the air to be much drier. We wanted that to be improved so that the breathing can be easier. And now I understand from the morning session that this is also good for the trees. They will also be more effective if there's water content in the air. More air, water content in the air. Okay, so what is the overall conclusion from the study that have been done? We have come out with all these strategies that you can see here, what is the impact that it has created in terms of air temperature. We could see a reduction of air temperature of about 0.8 to 2 degree difference in terms of the materials that we have used, and we got a slightly improved result in terms of air temperature when it comes to the trees. And these are overall conclusion. How we are presenting it to the municipality, because we are closely working with the local government to implement this in city. So, for example, let's say cool roof. It can be a passive strategy, how it is applied and what is the impact it is going to create, and by what means. So one of the reasons I also asked this question is we have to convey this to the decision makers. Decision makers are not happy with improvement in 0.8 or 1 degree improvement in temperature. What is 1 degree? How does it matter is the question that we get to hear. So if we say 10 degree improvement, that's substantial. They look at it in that way. But hardly we could see an improvement of about 1 degree or 1.5 degree is what we were able to observe. So instead of conveying like this, we thought we should write it down and say what is it happening, why those strategies are working better, and in what way this can be improvised. So we came out with a matrix as well. These are supposed to be the strategies used in the neighborhoods. So all the neighborhoods that has been studied has been mapped here, and all the strategies that we have tested has been listed here. So which strategy worked, which strategy was more effective, less effective, and for which some of the strategies we did not try. So that has been mentioned here. Finally, we are giving this as an output on neighborhood level interventions that the city can adapt. So, like I said, they don't understand the. Finally, the decision maker has to understand this. So they don't understand these numbers. So it has to be conveyed in a simple way, so that some of these strategies can be implemented. Okay, so for all 13 neighborhoods, we are coming out with a simplified representation of how these strategies can work and where these strategies can be implemented in that particular neighborhood. Like this, we have developed for all the 13 neighborhoods, and we have a landscape architect in our team. So he has developed context-specific landscapes, right from trees to shrubs and ground covers, which requires minimal maintenance and less water requirement, and which survives in such conditions. So that has been developed, and we'll be presenting it to the municipalities. As an experimental pilot project, we are suggesting that the city can implement these three strategies in coming summer to check its impact, and if the results are good, the same can be replicated and applied in other parts of the city as well. So we had presented this to the municipalities for taking up for further implementation. Thank you so much for listening. If you want to know a little bit more about the project, we have created a spatial data infrastructure based on the results that we have generated. You can log in and check here. Thank you.
Thank you, Dr. Faiz. Thank you so much for that wonderful presentation. Since we are 5 minutes behind, I think we should start with the next presentation. So, can we have Dr. Lily? Are you here?
Lily,
Yeah, she's there. So, please introduce her.
After the wonderful session of Dr. Faiz, now we are moving ahead for another session from Dr. Lily Rose. So her topic is thermal comfort and heat stress in outdoor urban environments, challenges and design implication. Now I would like to introduce our speaker, So Dr. Lily Rose is a distinguished academic and researcher with over 23 years of teaching and research experience in architecture and climate responsive design. She earned her PhD in architecture from the Faculty of Architecture and Planning, Anna University, with a specialization in urban heat island and thermal comfort studies in the Chennai metropolitan area. She holds a master's architecture and bachelor's architecture along with a graduate diploma in construction project management from NICMAR Pune. Her research interests span urban climate mapping, thermal comfort simulation and analysis, local climate zone mapping, sustainable design, vernacular architecture and conservation. She has presented her research in prestigious international forums including ICUC, ISBE, IFOU, APSA at the World Sustainable Building Conference. Dr. Lily Rose has received international recognition including with William P. Lowry Student Travel Award and the IAUC Conference Award sponsored by the European Space Agency, Japan. With an impressive academic record, she has published around 40 research articles, more than that I think, in reputed journals and conference proceeding. She also sought after expert speaker, having delivered invited lecture at NIASA FDPs. And beyond teaching and research, she has actively contributed to the profession by organizing FDPs in association with Council of Architecture and Intact Heritage. She is associated with multiple professional bodies and editorial boards, including being an active member of the International Association of Urban Climate, Global Outdoor Thermal Comfort Studies Working Group, and the life member of INTAC and the Indian Society of Remote Sensing. Presently, she is working as Dean Academic in SPA Vijayawada. Now, I would love to call Dr. Lily Rose ma'am to deliver her session. Thank you, ma'am.
Thank you, Dr. Prashanti. I think after Professor Matt's session for the past 4 days, I think whatever I'll be presenting today is just a drop in the ocean. But still, we have done few of such studies in Indian cities. I'll be presenting that. Let me just present my screen. I hope my screen is visible to everyone. Dr. Prashanti, am I audible? And
Yeah, now it's visible.
Yeah, ma'am. It is audible.
Thank you. So today I'll be just giving an overview of this thermal comfort studies, outdoor, especially focusing on outdoor thermal comfort studies that have been done in few of the Indian cities. To start with, I think all these have been discussed earlier as thermal comfort differs, the indoor thermal comfort differs with that of the outdoor thermal comfort, and most of it depend on the personal parameters and the meteorological parameters. So the parameters that are used basically as I think Professor Aya Vijayalakshmi had given a list of indices that are used both in indoor and outdoor thermal comfort studies. So this basically most of the studies are pertaining commonly used are PMV, PET, PIT and other things. So here we'll be focusing on all this. Why this is important is basically these studies would enhance the productivity. It has a significant impact on health. So we do have these thermal comfort affects the productivity, it affects the performance, it affects the learning and cognitive skills, health and well-being. So it is important in those. Just to give a brief on why indoor and outdoor are different. Indoor studies wherein we can have controlled temperature, controlled humidity. It's basically a steady state affair wherein all the indoor parameters can be controlled, and in the absence of direct solar radiation, wherein when it comes to outdoor comfort, it is very difficult because you cannot predict the outdoor state of environment. It's not in a steady state condition, and it depends. It also varies in terms of the expectation of individuals. And there are three basic parameters which differentiates indoor to outdoor conditions. Basically, in terms of physiological aspect, that is in terms of our adaptive nature, especially people tolerate a larger variation in climatic conditions in the outdoors when compared to indoors. Though we have been In India, we follow that somewhere around 24 to 28 or 24 to 30 degrees is a comfortable range when it comes to indoors. But then in terms of outdoors, we do tolerate up to 32 degrees, depending on the geographical region where the city is located. And there is also this thermophysiological aspect, which also affects basically based on your clothing level and based on the activity level. Suppose even during daytime, during hot summer day, we do see cricket matches which are being conducted in the afternoon, because their expectation is different, their mental state is different. So in all aspects, so the comfort ranges vary depending on the activity you perform. Then the steady state condition, which is basically the heat balance. So the outdoor comfort ranges are much wider when compared to the indoor comfort ranges. So these basically affects the activities that are performed in the outdoors. When it comes to necessary activities, irrespective of the outdoor condition, whether it is good or poor, we do perform the necessary activities. But when it comes to optional activities, it is significantly reduced when the quality of the outdoor environment and the comfort conditions are not appropriate. The optional activities are reduced significantly, but if it is enhanced, then the optional activities enhances. So, and there is minor variation in terms of social activities. So these uncomfortable outdoor environments results in spending less time in outdoor, and we hardly see people in the outdoors during daytime, and it reduces the social activities and also reduces the optional activities of visit to cafes or restaurants or any other outdoor spaces um, in terms of leisure or recreation. So to give a brief thing, in terms of indoor thermal comfort, the variation in terms of meteorological parameters are the ranges are quite less. So if you see the diurnal variation in indoor and compare that with outdoor, the diurnal variations are much higher in outdoor. So if you see here, basically we can see that the temperature varies. Sorry. So you can see the temperature varies from about 31 degrees to about 27 degrees. So there is a variation of about 4-degree variation. Similarly, there is a variation in terms of from about 23 percentage to about, from about 18 percentage to about 67 or 70 percentage of relative humidity. So these variations would create a different kind of thermal feeling or thermal sensation of in the human being. So basically, if you see, you can see within outdoor space, within a short space, spatial region, in terms of if you stand in between two buildings, there can be heavy wind speed, but if you just go to the street, the wind conditions completely differ. Similarly, you standing under the shade, the comfort condition differs. Standing directly under the sun, the comfort condition differs. So there is a lot of spatial variation in the outdoor condition when compared to indoor. So these temporal and spatial variation creates different kind of thermal perception and thermal sensation in the outdoors. And also the wind conditions. So in the indoors, anything beyond 1 or 1.5, people cannot withstand, and they find it quite uncomfortable. But in the outdoors, people can withstand ranging from about 2.5 meter per second wind speed to about 10 meter per second wind speed. So it depends on what activity you are performing, your comfort conditions differs. So when you're performing fast walking or when you perform jogging, you can even withstand a wind speed up to about 8 to 9 meters per second. But if you're just relaxing, if you're just sitting, then you can withstand up to about 2.5 meters per second. So this is the kind of variation in terms of wind speed that we feel or that we perceive in the outdoors. So to give a brief on again, depending on the latitude, depending on the driver temperature, relative humidity and wind speed, our comfort perception or sensation differs. This is an example of how the temperature and humidity behaves and how they yield to comfort conditions. If you see, this is in Lund, Sweden, wherein the tribal temperature variations are between 17 degrees Celsius to about 2 degrees Celsius, ranging from summer to winter. But you can see the relative humidity percentages that varies from about 66% to about 91%. So the relative humidity is quite high, but then we will not feel uncomfortable because the temperatures hardly crosses 20 degrees Celsius. Though the relative humidity is high, at lower temperatures we won't feel very humid, and it may not have a negative impact on the comfort condition. And you can also see the wind speeds here are quite high, ranging from 3 to 4 meters per second. So here it is the wind chill index that matters a lot rather than the humidex index that creates uncomfort feeling as such. So here if you see, this is the comfort condition. So you can see these these areas where you feel uncomfortable are mainly due to the higher wind speeds and not because of the higher humidity. Though the humidity is quite high here, the discomfort is mainly due to the wind speed and the temperatures and not because of humidity. Where in the same case, it was this is in case of Vijayawada. So all three examples that I've chosen are humid conditions. But then the first one is cold, humid. Here, this is hot and humid. You can see the temperature here ranges between 30, the maximum temperature is somewhere around 32 degrees and the minimum temperature is about 24 degrees. So we just have roughly around 8-degree variation between winter and summer. But the humidity ranges, if you see, it ranges from about 61% to about 81%. So though the humidity is lesser when compared to Lund, which is a cold, humid place, here the issue in terms of comfort is mainly due to the humidity and higher temperature. So the high temperature and higher humidity is causing the discomfort. And you can also see that temperatures here, the wind speed is hardly 1 to 2 meters per second. So the wind speed is lesser. The discomfort is mainly due to the higher temperatures and higher level of humidity. So here we can see these humidities, especially the temperature ranges. If you see here, it is somewhere around 22 degrees Celsius to around 26 degrees Celsius. Even at that particular 22 or 26 degrees Celsius, we would find discomfort mainly because of higher humidities ranging at around 70% or 80%. This would cause a lot of discomfort in terms of outdoor conditions. So this is another place. This is Hong Kong. So this is basically warm and humid climate, where you can see the temperatures are basically ranging between 16 degrees Celsius to about 30 degrees Celsius in summer. And here again, the variation in relative humidity is similar to what we saw in Vijayawada. This is somewhere between 65 to 76%. But then here the comfort conditions are comparatively better to Vijayawada, though the temperature ranges are 30 degrees and the relative humidity is similar to what we experience in Vijayawada. Here the temperature ranges are different, but then the higher wind speed, 3 to 4 or 5 meters per second causes enhances the comfort. So you can see here the comfort range is a lot of lines within the comfort range are mainly because of higher wind speeds. So here the issue, what we need to look at it is not just the values, it is a combination of the temperature, the humidity and the wind speed. In cold climates, the wind speed creates a lot of wind chill index, but in hot climates, the humidity and higher temperatures lead to a lot of discomfort. So I think these things we have already discussed. The mean radiant temperature, basically when it comes to outdoors, during daytime we gain a lot of temperature, like Dr. Fayez was mentioning, during daytime the MRT increase. So it is basically the reflected radiation that one perceives during daytime. That's basically, so that would create a lot of heat gain in human body. During night, in the absence of solar radiation, we will lose heat to the atmosphere. So this is important. So mean radiant temperature is an important index which we need to look at, because that would define whether we are going to gain heat or lose heat to the environment. And as I mentioned, the temperatures, though the temperatures, if you see here in all three cases, the temperature is only 20 degrees Celsius, but the weather at that particular time. So this MRT also predominantly based on the weather condition on a particular day. So if you see at 20 degrees Celsius, if it's cloudy and calm, we would feel the same temperature. But the same 20 degrees Celsius, when we have higher solar radiation, which would result in higher MRT, which would result in heat gain, though there is no wind speed, we would feel a temperature of about 30 degrees Celsius. This is basically the our comfort index in terms of PET. So the higher solar radiation, we would gain a lot of heat. So we would feel as if it is 30 degrees Celsius. Similarly, with 20 degrees Celsius, when it is cloudy and if it is windy, then we would feel, though it is 20 degrees Celsius, because of higher wind speed, we would expect as if it is 15 degrees Celsius. So it also depends, the comfort also depends on the weather condition on that particular moment. So that also affects our comfort feeling or comfort sensation. So basically these outdoor thermal comfort studies, I think we have there are a lot of studies that have been done in terms of field surveys, then field measurements and simulation, which we have seen in all these 4 days. Here, these are the threshold values that have been. So how do we feel? Because the thermal sensation analysis in indoor differs from that of outdoors. So we can, here you can see, this is a standard threshold values defined by Matsarakis. Basically here it ranges from less than 4 to 41 degrees Celsius. Anything beyond 41 degrees Celsius is termed as extreme heat stress. Anything less than 8 degree Celsius is termed as strong cold stress. So the generally here it is defined as 18 to 23 is the comfortable range. But this would differ in terms of Indian cities. So this is a study that has been done by Kodarkar, wherein we have defined the comfortable ranges have been defined for Indian cities where we feel extremely hot, especially in the tropics. So it ranges from, wherein in the previous study it is ranging from about 18 to 23. Here we are they have found that the comfortable ranges vary between 26 to 30 degrees Celsius, wherein there is no thermal stress. Anything beyond 50 or 51, it is termed as extreme heat stress, wherein in the previous other studies in other countries, it was only 41 degree. So here, the heat stress varies from about 32 to 51 degree. It is categorized into slight heat stress, moderate heat stress, and strong heat stress. So these again, it varies based on the thermal sensation scale and thermal comfort scale, as well as thermal tolerance scale. So based on the number of points that you analyze, accordingly the ranges vary and it differs. So based on these, now we just go through some of the studies how these heat stress in outdoors could be mitigated through some design strategies. I think morning Professor Matt has given an elaborate indication of these landscape strategies, wherein these impacts, so if you see having a ground cover, I think even in Dr. Fay's study, we just realized the ground cover could not provide a lot of comfort. So the impact of ground cover is only to a range of about 10 meters, wherein the impact of group of trees and shrubs, it can impact the microclimate up to a range of about 60 meters. Similarly, the materials, I think yesterday we had Professor Matt presenting on a lot of these cool materials, how these There were a list of 9 phase of materials which he discussed. So these materials used in pavement can also vary the outdoor thermal comfort. So and the ranges varies from local to city level. So integration of artificial structures like green wall, green roof, fountains can affect at the local scale. At the street level, we can have the height to width ratio, which can impact the wind movement within the street level. At the public parks or open spaces, the tree canopy, ground cover, water catchment features at the urban draining level. And then at the city scale, the reflective materials on roofs, which we had seen several such case studies, which was presented by Professor Matt yesterday. So these will have an impact at the city scale. So the intervention can range from local to city scale, which can have a significant impact on cooling. Similarly, at the neighborhood level, we can either have canopies. I think we did see Professor Dr. Fayez mentioning about spacing between tree canopy. So that also matters because that also reduces the sky view factor. So which will also have an impact on thermal comfort. The portion of the um, uh, canopy that shade that will have better cooling when compared to areas that are completely exposed to sun. So then these kind of temporary shading structure, yesterday Professor Matt was mentioning about the dynamic shading structure, movable shading structure. We can either have static or dynamic, and the shade of these structure which falls throughout the day varies from morning to evening. So you can create these areas can be shaded. It cannot be shaded. It will not be shaded throughout the day, but at some point of the day, the shade keeps on moving. So the pattern of usage of these outdoor space can also vary based on the shading ranges. So exposed areas again can be enhanced by means of introducing water features so that it can add some kind of humidity into the atmosphere. Um, there are also other studies, like we had discussed a lot of these in hot and arid climates. Here again, strategies from 50% grass along with trees, 50% grass with 25% trees, and 50% grass with 50% trees, and 75% trees are underlined. Here again, we can see when getting into these are basically simulated studies using NVMet software. We did mention these on-site measurements are important. Dr. Fayez also mentioned that these are important when we use simulation studies because it requires the validation is important. So when we simulate in softwares, we have to collect on-site measurements and validate those. Different strategies were analyzed, and the best strategies that improves the outdoor thermal performance were analyzed. Again, the parameters that are analyzed are like varies from individual meteorological parameters like air temperature and humidity, and also the comfort indices in terms of MRT, PET, UTCI, all that can be analyzed. So again, these are different strategies wherein we can see first in a neighborhood they just improved only 50% grass cover. The second strategy 50%, the scenario basically 50% with 25% green cover. Then the third one 50% ground cover and 50% green cover, and 50% ground cover and 75% green cover. So they performed this in a neighborhood, and the selected trees basically depends on the parameters that they have chosen are leaf area density, foliage height, leaf area index, and albedo. So these were selected, and then within these they've selected different within the neighborhood in different scenarios. They've selected 4 points. One location where they had pavement and tree only on shade on one side. Another location wherein it is between two building surface with asphalt road. Another location between two buildings but it has a pavement. Then the location where there is a green cover, grass, wherein the number of trees, the tree canopy has been increased again between. So they try to analyze these. So this is at location R1. how it performed in all three scenarios that were analyzed. So we can see that this is again our temperature reduction in terms of Kelvin. The temperature reduced during nights till about 6 a.m. Then it started increasing, and this again depends on the sun angle. This reduction after 6 a.m. to 12 a.m. Depends on the shade, mutual shading between buildings, and also depends on the sun angle, and it just elevates in the afternoon and then it decreases. And this varies with point to point depending on the shading condition in the night. So here you can see it reduced to about 0.2, wherein here the reduction is only till about 0.4. So this is R2, which is this location, because again the tree did not reduce it. Here it is just open. So the reduction we can see up to 0.2, and there are some spaces of which are exposed to the sky, so it can radiate back. So again you can also see the reduction here. When it's here it is somewhere around 0.5 reduction in the night, ranging from 0.2 to about 0.5. As the density increases, you can see as the density increases, this is wherein 50% grass cover and 50% tree cover. So the temperature reduction is also enhanced mainly because of increase in relative humidity, this being an arid condition in Egypt. So these are different scenarios and different points. So you can see a reduction here of about, this is the base case, and you can see a reduction of from about 70 degrees to about 55, around 15 degrees Celsius reduction is there, but the behavior differs. Here it is only one side tree and it is a pavement. Here it is two side tree with asphalt. So here the second scenario did not perform well, but the other three scenarios performed well. Wherein here, which has ground cover, and then trees with ground cover and trees with pavement. So the ground cover matters a lot in terms of heat that is being radiated back into the atmosphere. Then these are some of the studies that have been done in Chennai. Now we'll just move on to some of the studies that have been done in India. So this is a study that was done in Chennai, a region called Tyagaraja Nagar, which is a mixed residential neighborhood. Here, similar to Dr. Faiz, we have taken 3 LZZ locations within Chennai, wherein this we try to analyze how the building regulations impact outdoor comfort conditions. So the first case provided the existing building regulations. So we just assumed that maximum built up with the existing building regulations. Then the same thing was introduced with increasing height and reducing the plot coverage. So that was the development regulations in Chennai was modified in 2019. So we tried to see what would be the impact of this modified building regulation, which had increased building height and increased FSI, while the plot coverage was reduced. So that gave way for a lot of open space at the site level, wherein here we consider the existing vegetation itself. And in case 3, we increased the open spaces that were available at the plot, converted 50% of that into vegetation and trees, which are planted at an interval of 6 meter to 9 meter. So this increased the permeable surface fraction and the green cover fraction. So these were the 3 scenarios that were analyzed to find out which had the maximum enhanced outdoor thermal comfort conditions. So these were the 3 locations. And then in the first case, we could see these are the parameters as per the LCZ classification. So we analyze the sky view factor, the aspect ratio, the building surface fraction, impervious surface fraction, pervious surface fraction, height of roughness element. So if we see this, the height of roughness element increased with building height. So if you see here, the height of roughness element are lesser because wherein the building heights were much less. In case 2, the building heights were increased, but then vegetation was not increased. So the roughness element increased in the case 2, wherein here the building heights are increased and plot coverage increased, but retaining of existing vegetation. In case 3, the green surface fraction was increased, which increased the permeable surface fraction. So you can see that the impervious surface fraction is the pervious surface fraction is increased significantly from the case 2, and the impervious surface fraction has reduced from case 2. So this enhanced the comfort. So we just try to analyze this, and these were plotted. So based on this analysis, so the sky view factor again varied, because as the building height increases and the plot coverage reduced, the view to the sky also increased. So this is location A in the third level with lesser building and increased plot cover, the view to the sky was increased. So we can see that in the first case, which was the base case, the number of hours of extreme heat stress, this extreme heat stress is as per greater than 50 degrees Celsius, which is based on PET values. So you can see number of hours of heat stress in the base case was just 7 hours in the base case. In the improved case, with 50% conversion of the plot area into grass cover and permeable surfaces, the extreme heat stress is completely reduced, and it is just gone into the moderate heat stress of 46 to 50 degrees Celsius, which was considered as moderate heat stress as per the recent study in India. So this has reduced the number of extreme heat stress in all 3 locations. So even in location B, which had just 2 hours of extreme heat stress, is completely reduced, and it doesn't even have moderate heat stress. It just reduced to only so this has significantly reduced to moderate heat stress or strong heat stress. So you can see that the duration of extreme heat stress has been significantly reduced in the modified building regulation by increasing the building height. Again, this depends on the compactness of the neighborhood. If it is compact, then that would vary. So if you see here, the LCZ classification varied with varying the building regulation. This was open mid-rise, and then location A remained open mid-rise, but in location B and C, which was a compact low-rise in the existing condition, was modified to compact mid-rise because of building height, and which was an open low-rise in location C has modified to open mid-rise because we had increased the building height but then increased the pervious fraction. So the local climate zone classification also varied. So that also will have an impact on the enhanced comfort conditions. So the next study is basically, this was done at Ahmedabad, wherein we did try varying varying the building heights in gated communities. So there is in Ahmedabad, especially near Charodi region, where the high-rise buildings started cropping up in the recent decade. So we analyzed what is the aspect ratio in the high-rise high-rise housing, which is a gated community, and we categorize them into 3 aspect ratio ranges. So aspect ratio range of 1 to 1.5, then aspect ratio range 2 is 2 to 3, and aspect ratio range 3 is 4.5 and 5, and we found majority of the buildings fall under the category of aspect ratio range 2 to 3. So we chose one of the high-rise housing in that range 2 to 3, and we measured on-site data, and we tried to validate through NVMET simulation, and we found a good correlation. Then we varied various scenarios by varying the building height. First, we tried to vary the building heights in northwest and southeast orientation. Then we modified the variation in southwest and northeast orientations. Then we introduced shading blocks between buildings. It could be, this was in terms of just a pergola or a shade. It is not floor. It is just the shade between the buildings. Like because we did realize that shading enhanced outdoor thermal comfort, then we introduced it in the northwest southeast blocks. Then the similar thing was introduced in the southwest northeast blocks also. Then we varied all the heights of all the buildings, and we just analyzed these in NVMET simulation. Uh, we did do the analysis for both critical summer and winter conditions for the entire day. So this realize, if you see, the first one was just higher building in southwest northeast, and the second one is north west and southwest southeast. So the third one with shading, then with shading in the other orientation. So we did find from the base case had about 6 hours of extreme heat stress, that reduced to about 5 hours of extreme heat stress, though it is just 1 hour. But then the variation, if you see, it is reduced to about 2 degrees Celsius. So from 52.4, it reduced to about 50.4, which is a significant reduction in terms of PET values, 2 degrees Celsius. But the same thing in winter, when we saw, the winter also, they did have extreme heat stress of about 5 hours, which was significantly reduced to 3 hours in scenario 4 and 5. But then if you see scenario 3, though it had 6 hours of extreme heat stress, but in winter it was quite comfortable. So overall, scenario 3 performed better. But then here again, we had a similar reduction of about 2 degrees Celsius, though it is the number of hours is same, but then reduction is significant. So these analysis has to be done for both summer and winter. Doing it only for summer may not be effective, because we have to take it for a annual basis. So this was done, and then we did try to, using the best performing scenario, we did modify the same thing. So the existing was uniform height of all 4 blocks. Then we oriented in the best orientation with this northwest southeast. Then in the we just increased the height in the northwest, and then introduce a shading block in the northwest, introduce another shading block in the southeast. Then we perform the final. This was the proposed scenario. So this again was analyzed between the other case scenarios, and this proposed scenario, which varied building height in all. Here, when we vary the building height, there was just one consideration was considered. We had kept the FSI constant. We did not increase or decrease the FSI. FSI was kept constant. Only certain relaxation in building height was given. So normally in development regulation, there will be a restriction on maximum height to be built. So this we just relaxed to find out how this could enhance the comfort condition. It was not maintained as per the development regulation, but FSI was kept constant. Certain amount of relaxation were given in building height, but we did consider the air corridor and all that. That was not, it was not in the air corridor. So the height were increased, but then FSI were kept constant. So the saleable area remained the same. That did not vary. So with that variation, we could reduce from about 6 hours of extreme heat stress to about 3 hours of extreme heat stress, and significant reduction in terms of 2 degrees Celsius in the PET. And we also, that it also had impact on moderate and see, there is an increase in moderate and strong heat stress, because we had reduced from extreme heat stress has gone to moderate heat stress and strong heat stress. Similar analysis was performed for winter also, and we found that the scenario had just 1 hour of extreme heat stress, but then predominantly throughout the day this was comfortable. So based on this, we suggest that varying building height, but maintaining the FSI, which is in terms of asymmetrical canyons, depending on the location. Here in Ahmedabad, the northwest and the southeast orientation performed better. So these were the findings of the study. So we could see a reduction of PET from 53.7 degrees to 39.3 degrees. This is in winter and this is in summer. So this, and then because of the proposed no, this is in summer. So you can see this was reduced to about 39.3 degrees Celsius, and our MRT was significantly reduced. And even the PET in winter in the proposed state reduced to 32.7 from 59.7 in the existing scenario. So the proposal of 3:2 aspect ratio and northwest southeast orientation work better in Ahmedabad scenario. But this would vary depending on the local geographic location and the wind direction. All that matters, makes an important needs to be considered for final recommendation as such. This is another study which was done in Vijayawada, which is again an hot humid climate zone, where we try to analyze the impact of sky view factor. Here also we vary the percentage of green cover and grass. Here we took two narrow, this is again a high-rise neighborhood wherein two pathways within the neighborhood which had a sky view factor of 0.224 and 0.342 ways. This is the mean pathway and this is the space between buildings. We try to analyze how this could improve the thermal comfort conditions outdoor. So, is there some question or
Can take some questions actually. Anybody has questions? Ma'am's work is so we can ask questions, unlike Dr. Maths. So if you have any doubts, please feel free to ask.
any questions?
Yeah, no questions?
Can I continue?
Raghav. Anybody? Raghavi, are you trying to ask something? If you're trying to ask, please ask or type in the chat box. Else, please mute yourself because we are not understanding whether you want to ask anything. I'm not able to understand. Either people, please either ask question or mute yourself because we are not hearing anything with clarity. Raghavi, Miss Raghavi Ilangovan, please mute yourself or ask your question. If you don't have a question, please mute yourself. The speaker is not able to understand whether you want to ask a question and then it is hampered. The talk is stopped now. Miss Raghavi, please mute yourself. Doesn't look like she wants to ask any question. Okay. No chat box.
No. Okay. Can I continue?
Yeah, we can continue.
Yeah. So this study again, we analyze different scenarios and also we analyze different orientation of this particular neighborhood. This is the typical which had 5 blocks and a club house. Actually, the existing had 6 blocks. We removed 1 block to create space for open space there. So this is the kind of scenario that we analyze. The first scenario was 20% tree cover. So we analyzed in different
Madam, please, Ms. Raghavi Ilangovan, please mute yourself. Sorry, madam, continue and write in the chat box.
Yeah. So
She's
we did
muted.
analyze 20% tree cover with different orientation, rotating this to identify which orientation works the best. And then we analyzed the same for various parameters like air temperature, mean radiant temperature, and PET. And we found that the 225-degree orientation, that is the south, oh sorry, 225-degree orientation, which is the southwest orientation, worked the better because that created mutual shade between buildings, so which enhanced the thermal comfort. So then we did analyze for 50% tree cover. Similarly, we oriented and we found here the 135-degree orientation, that is basically the southeast orientation worked better. Similarly, 70% grass cover. We did not go in for 70% tree cover because that completely covered the sky. So we tried to analyze. This was taken from previous literature. Then we analyzed 70% grass cover. So this again gave 225 as the best performing orientation. So based on this, we did analyze PET. So we can see that 50% tree cover and 20% tree cover more or less perform better. But then here the reduction is significant from 52 to 48.2. So it's roughly around 4 to 5 degree reduction was there in 50% tree cover. Wherein 20% tree cover, we could get 2-degree reduction. Here, if you see 70% grass cover, there was no reduction. Instead, it increased the PET values, as we saw in Dr. Fai's study also. So the grass cover, suggesting grass cover actually increases the PET value, and it also increases MRT value. So it is always better to go in for trees, a combination of tree shrub, but then grass cover beneath the shade may work better, but then exposed to sky may not work better. So this is the analysis, and we can see that a temperature reduction of 1 degree Celsius up to 1 degree Celsius was derived from 50% tree cover, and a temperature reduction of only 0.1 degree Celsius was there in terms of 20% tree cover, and the temperature increased in 70% grass cover. Similarly, in terms of MRT, there is a reduction of about 4.75 degrees Celsius in terms of 50% tree cover, and it was 3.25 degrees in 20% tree cover, and the temperature increased in 70% grass cover. Similarly, a reduction of 2.5 degrees Celsius was observed in terms of 50% tree cover in PET, and 1.6 degrees Celsius in terms of 20% tree cover, and the temperature increased in 70% grass cover. So the study, after doing this, we realized that a reduction of 1 degree Celsius with 50% tree cover, how this could impact the energy consumption in indoor. So we just model using this meteorological condition at this scenario. We reduce the values of our temperature by 1 degree in the microclimate in design in the EPW5, and then we ran the simulation in Design Builder to find the energy consumption, the indoor energy consumption pattern during summer and winter. And we categorized the building into 3 levels: the lower levels, middle floor levels, and upper floor levels, because the energy consumption pattern also varied with the number of increase in floors. So we can see that during summer, though the reduction, this is just done for 1 day, but it has to be done for monthly basis. We just ran the simulation for 1 day for want of time, but then this, if it is run for a month, then this can be run better. So here we just multiply that into number of units for a monthly basis, and we found that this is the saving on a monthly basis at different floor levels. Though this is lesser, the cost during summer depends on the total number of energy consumed per month. So energy units consumed, as the number of unit increases, the cost is also increased, because of which this is the savings that we get got during the study, and it varies, and it is the saving is much higher at higher floors when compared to lower floors. Similarly, in winter, the savings were much higher. So the reduction in number of units is much higher, but it is more or less the same in all the floors. But since in winter the total number of units consumed are much lesser when compared to summer, the cost reduction is per unit is much lesser. But then if you can get much better significant reduction in winter when compared to summer, because the summer temperatures in Vijayawada are quite high. It ranges from about 38 degrees to about 43-44 degrees during daytime. So without air conditioning during daytime, it is not at all possible to stay indoors. Because of that, the summertime savings are much lesser. But in winter, if the microclimate is modified, that can enhance the energy consumption, that can reduce the energy consumption pattern, and it can enhance the energy savings. So we can save much, because the summer temperatures in Vijayawada is somewhere around 34 degrees Celsius, and if that can be reduced by about 1 degree Celsius, then it will have significant impact on energy savings as such. So this was another study done at Vijayawada. So we can see the savings in terms of, so the middle floor had better savings in summer, wherein the upper floors had higher savings during winter. So here, as far as Vijayawada is concerned, the 135-degree north orientation, that's basically the southeast orientation, enhanced comfort. That's mainly, it minimized sunlight exposure and it maximized the wind speed. Being hot and humid, the wind speed played a significant effect in enhancing outdoor thermal comfort. And generally, these gated communities had a maximum building height of 24 meters. So a 13-meter spacing was suggested between buildings, which will include 2.5 meter spacing between buildings and the vehicular movement or the road. So that can provide, that can integrate greeneries or vegetation or trees within the gated community, which can enhance the thermal comfort conditions, especially in the outdoor, which will again have an impact on indoor energy consumption also, that can be reduced significantly. So that was the finding of this particular study. And there's another study which was done at Ahmedabad, especially in low income settlements. Here, it was found as a hotspot in Ahmedabad. We analyzed roof level, pavement level, and at the wall levels. So we modified different materials in the roof, which had higher albedo of 0.7 and 0.8, 0.95. Then we also had medium albedo in terms of 0.3, 0.3. These are the different materials that we use. So we mainly, the study had concentrated on higher albedo. So we just categorize. HR indicates higher albedo, M indicates medium albedo. So L indicates low albedo. So these were the options that were used in pavements, walls, and then roofs. So then we tried to replace it with the existing condition, which had brick wall and GA sheet roofing, and some of them had asbestos, cement, and concrete pavement and bare soil. These were the existing conditions. So we did simulate different conditions here. So here, the first case was medium albedo in wall, medium albedo in roof, and low albedo in pavement. And these were the mean radiant temperature values. So here, these options or scenarios which had medium albedo in wall, lower albedo in wall perform better with lower pavement. So here we realize that the walls and pavement should have predominantly lower albedo, as they reflect heat onto the streets. And the roof, since this is a low-rise development, this suggested medium albedo is much better. So if you see here, from here there is a reduction of about 1 degree, but then though 1 degree reduction is very less, but we can see this reduction in terms of MRT was reflected radiation, it was much better. So the other three clusters wherein we can see here the medium albedo involved, the medium roof and medium pavement perform better. So we can see that the maximum temperature, the ranges have predominantly, these are just moderate with just 1 hour with extreme heat stress. So we are just looking at the number of hours of extreme heat stress, reduction in that, because you cannot reduce the heat stress throughout the day. So the intent is to reduce the total number of hours of extreme heat stress rather than looking at removing heat stress from that location. That is not possible with the higher temperatures and humidity that are experienced in tropical regions. So here we were able to reduce the extreme heat stress to just 1 hour from the base case, which was approximately 4 hours. So that is the kind of approach we had done it. Here again, in this particular cluster, we could again medium albedo work better. So this study suggested that low-rise informal settlements going in for higher albedo, as they reflect heat into the atmosphere and which are trapped, it acts as a heat trap, and due to convection at the lower level, the street level temperature or the mean radiant temperature comfort level was very hot. So if in high rise, then going for higher albedo is better, but in low rise, especially G+1 structure, going for higher albedo in the roof may, due to convection, it might increase the heat sensation on the street. That was the finding in this particular study. Yes, I think with this, I would stop here. Thank you for your attention. If there are any questions, I can just.
Anybody has any queries, any questions, or any aspects to discuss?
Yeah, good afternoon.
Good afternoon.
Yeah, I have one question actually, ma'am. You have talked about the indoor thermal comfort and outdoor also.
Yes.
In Indian context, do we have any national standard for indoor thermal comfort, like say in RCC roof or tile roof or tin roof? The temperature should be range between this degrees Celsius, and that need to be followed by different departments like housing department.
No.
Do we have? Yeah.
No, we do have standards in terms of thermal comfort range, indoor thermal comfort range. But in
Okay.
terms of temperature of materials, we do see this is basically defined in terms of thermal comfort range rather than the temperature on material. You're talking about the surface temperature and different
Yes.
materials. Because that does not define that, because again thermal comfort depends on the overall comfort range. So we'll have to follow the thermal comfort range. IMAC stipulates operating temperature for various cities. So based on that, based on IMAC only, we analyze these studies. So we did, based on the operating temperature range, we were trying to see whether modifying these material assembly in the building envelope can enhance the comfort within, can bring down the comfort within that comfort range. That is the
Okay.
intent.
Okay.
But in terms of surface temperatures, there is no standard as such. But in terms of comfort ranges, there are standards. ASHRAE standards are followed, and for Indian cities, IMAC is generally adopted.
Okay. Thank you.
I think so Vijay Lakshmi can add on to it because it's on indoor thermal comfort.
It's your day, ma'am. Enjoy. I'm like dumbfounded after the first class.
Yeah.
I
How
think
to select the appropriate thermal comfort index for city scale that works both indoor and outdoor. See, the thermal comfort index, it depends on the climate type basically. So, not all thermal comfort indexes suit the different climate types. So, for especially humid climate, the index that includes humidity as an aspect need to be considered. So, generally, for tropical cities, PET, UTCI are generally adopted for outdoor thermal comfort, as well as in terms of indoor thermal comfort, it is basically the operative temperature which we use. Yes, Aishi, did I answer your question? Miss Aishi?
Yes, thank you, ma'am. Yeah. But, ma'am, in addition to that, I also wanted to know, say, if I'm comparing between the city level phenomenon of across different climate zones, would I need to calibrate those values so as to say this is equivalently comfortable or something?
Within the same city, you're trying to say at different neighborhoods?
No, yeah, that, and also for different climate zones, for cities in different climate zones, if I am to compare the comfortable conditions.
So different climate zones will have different comfort ranges. So you'll have to first identify the comfort ranges for that particular climate zone or for that particular city. And then you'll have to compare your results with that particular comfort ranges. For example, in Vijayawada, even 32 degrees, 31.5 is considered as comfortable in terms of outdoors. But for indoors, we don't go beyond 28. So it all depends on the comfort range. Cities and the type, whether it is in indoors, it depends on whether it is a naturally ventilated building or if it is a conditioned space. So based on that, the comfort ranges differ. So based on your study condition and based on your assumption, you'll have to derive those comfort ranges and then compare your findings.
Okay, thank you, ma'am. Yeah, got it.
Any other question? Dr. Vijay Lakshmi, Dr. Prashanti,
Yeah.
there
Yeah,
are no
yeah.
questions,
So,
can we wind up?
yeah, okay. Since there are no more questions, thank you, Dr. Lily and Dr. Faiz. Thank you so much. And we will meet again tomorrow, which will be the last day of the GIAN program. It will be the 5th day. So please be on time. Otherwise, you will miss important things that are told. Okay. So be on time and we will meet tomorrow. Thank you. So tomorrow's session starts at 11. It's only by Sir and it is 11 to 1. So be on time tomorrow. Thank you. So, join at 11 o'clock tomorrow, 11 to 1, and then we'll have a small valediction which is online. Thank you, Brindaji. Thank you so much. Bye. So I will log off. Thank you.